Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are vast and the pace is slow enough not to jolt you out of your pillow cocoon. As the world outside perhaps quiets down, let us invite our thoughts to gently wander like clouds across a vast evening sky. Tonight we're going to tiptoe into one of the most profound stories our planet tells, the tale of its rhythms, its gentle breaths, and its grand ancient dances. How does our Earth, this vibrant living sphere, orchestrate the countless subtle shifts that shape our days, our seasons, and even the deepest currents of its long history? But don't worry, we'll take it slow. This isn't a race through complex equations or a hurried dash through scientific names. It's more like floating through a galaxy of ideas with a cup of chamomile tea, allowing wonder to be our guide and the soft hum of discovery to lull us into a deeper understanding of the world beneath our feet and the cosmic ballet above. As we settle into this quiet space, let us first consider the familiar rhythms that weave through the very fabric of our earthly existence. There is the gentle turning of day into night, a celestial clockwork that has guided life since its very first stirrings. We wake with the dawn bathed in the soft, hopeful light of morning and drift into slumber as twilight deepens, painting the sky with hues of lavender and rose. This daily dance is so fundamental, so reliably comforting, that we rarely pause to truly marvel at its profound predictability. Yet it is the most elemental of Earth's cycles, a constant whisper of order in a vast universe. Each sunrise feels like a quiet reassurance, a gentle promise whispered across the horizon that the light will always return. And each sunset, a soft invitation to rest, to let go and to trust in the unseen forces that turn our world. This simple oscillation between light and shadow shapes our biology, our routines, and even the cadence of our thoughts. We are creatures of these rhythms, our inner clocks attuned to the planet's steady spin. The moon, a silent companion, watches over this daily transformation, its silvery light often mirroring the sun's warmth in a softer, more mysterious glow. It's a dance performed without a sound, yet its presence is felt in every living thing, from the blooming of night flowers to the waking of nocturnal creatures. And then there are the changing seasons, a grander, slower ballet across the year. We witness the tender green shoots of spring unfurl, bursting forth with new life after winter's long sleep. This is a time of gentle awakening, a fresh canvas painted with vibrant pastels. Then comes the vibrant energy of summer's full bloom, a season of warmth and abundance, where the sun holds court in the sky for longer hours, inviting us outdoors into its golden embrace. The air hums with the busy life of insects, and the scent of blossoms fills the breeze. As the earth continues its graceful journey, we move into the rich, fiery tapestry of autumn leaves, a breathtaking display of nature's artistry, as the greens turn to gold russet and deep crimson. This is a time of turning inward, of gathering, of preparing for what is to come. And finally, the hushed, crystalline stillness of winter's embrace descends, blanketing the world in white, a time for rest, reflection, and quiet introspection. Each season brings its own unique palette of colors, its distinct melodies of birdsong or the soft crunch of snow underfoot, and its particular scent carried on the wind. This predictable progression, too, is a comfort, a reminder that growth and rest, warmth and coolness are all part of an unending, graceful flow. We mark our lives by these turning points, planting seeds with spring's promise, gathering harvests under autumn's golden light, finding quiet warmth in winter's stillness. They are the chapters of our year, written by the sun's patient hand, an epic poem unfolding with each turn of the calendar. The changing angle of the sun, a subtle tilt of our planet's axis, orchestrates this magnificent display, dictating where warmth will linger and where coolness will settle. And if we listen closely to the murmur of the sea, we can discern yet another ancient rhythm, the ebb and flow of the tides. The ocean, a vast, restless heart, breathes in and out, drawing water towards the shore and then releasing it back to the deep. This colossal movement, orchestrated by the moon's silent gravitational pull, reshapes coastlines twice a day, every day without fail. Imagine the moon, our closest celestial neighbor, like a gentle, invisible hand subtly pulling the great oceans, creating bulges of water that follow its path across the globe. As our Earth spins beneath these bulges, coastal areas experience the rise and fall of the tide. It is a powerful, yet gentle reminder of the invisible forces that govern our world, pulling and pushing with a delicate, unwavering strength. The tides are a lullaby sung by the cosmos, a soft invitation to surrender to forces larger than ourselves, to acknowledge the deep interconnectedness of our planet with its lunar companion. For coastal communities, this rhythm is not just a beautiful spectacle. It dictates fishing schedules, navigation, and even the architecture of their lives, a constant reminder of the ocean's immutable power and grace. The shifting sands, the ever-changing shoreline, all speak of this ceaseless rhythmic breath of the sea. These familiar cycles, day and night seasons and tides, happen over relatively short periods, easily observed and precisely predicted. We build our lives around them, trusting in the sun's return, the spring's renewal, the ocean's gentle pulse. They are the visible threads in the tapestry of our world, comforting in their regularity. Their predictability allows for the intricate dance of life to flourish, for ecosystems to thrive in expected patterns, for species to evolve in harmony with these reliable shifts. We rely on them instinctively, a deep primal trust in the Earth's steady turning. This understanding of short-term cycles is like reading the familiar comforting sentences in a well-loved book. They are immediate, tangible, and provide a sense of stability to our fleeting existence. But now let us allow our thoughts to drift a little further beyond the immediate horizons of our daily experience. For our planet, this magnificent home is also influenced by other cycles, grander and more elusive, affecting its very essence over much vaster intervals of time. These are the deep breaths of Earth, the slow, deliberate movements of its colossal engine, which can be far trickier to forecast their whispers, almost imperceptible to our fleeting lives. They are like the deep currents of a vast ocean, hidden beneath the surface, yet profoundly shaping everything above. Imagine these as the subtle shifts in a grand symphony, notes so long and drawn out that our ears accustomed to quick melodies can barely perceive their unfolding. They are the background hum of geological time, the long, slow exhalations and inhalations of a planet living on scales we can barely comprehend. These cycles whisper of change not over days or years, but over millennia, over epochs, shaping the very face of continents and the flow of ancient rivers of ice. Their influence is cumulative, building up over vast stretches of time, like the slow, patient erosion of a mountain range by a persistent, gentle breeze. One such cosmic waltz, for instance, is the Milankovitch cycles. Imagine our Earth not just orbiting the sun, but performing a subtle, elegant dance in space, a slow, majestic ballet where its tilt, its wobble, and the very shape of its path around our star change ever so slightly over tens of thousands of years. These gentle shifts, these imperceptible adjustments in Earth's cosmic posture, are believed to play a profound role in the ebb and flow of monumental ice ages, vast periods when much of our planet was cloaked in a glistening mantle of ice, punctuated by warmer intervals like the one we are in now. Think of Earth as a top spinning on an uneven surface, its axis occasionally leaning a little more, or its circle around the sun stretching into a slight oval. These tiny cosmic nudges over immense periods can alter the amount of sunlight reaching different parts of the planet, particularly at the poles. They are the deep, slow sighs of the planet, barely audible across millennia. A story written in ice and ancient rock, a testament to the patient, persistent forces of the cosmos. But these are cycles of such immense duration, so stretched across the vast tapestry of geological time, that it is truly unlikely our own brief lives will ever feel their direct, chilling touch. We are but fleeting visitors on this grand stage, observing the very end of a single scene in a play that spans eons. Yet there is one such grand climate cycle, a powerful rhythm born in the heart of the Pacific Ocean that will most certainly unequivocally touch your life. It is a phenomenon known by a name that sounds almost mythical, steeped in the ancient lore of seafarers and the whispers of the wind, the El Niño Southern Oscillation, or ENSO for short. This is not just a scientific term, it carries with it the echoes of ancient wonder, a phenomenon that became the stuff of legend centuries before our science could even begin to unravel its intricate mechanisms. It is a tale that speaks of the deep human need to understand and name the powerful forces that shape our existence long before we had the instruments to measure them. El Niño and its counterpart, La Niña, are not merely local weather quirks. They are colossal pulses like the beating of a giant watery heart in the Pacific, whose profound impacts are felt nearly everywhere on Earth. Imagine a stone dropped into the deepest ocean, the ripples spread touching every distant shore. So it is with ENSO. These vast oceanic shifts can rewrite the weather patterns across continents, bringing unexpected floods to one region and parching droughts to another. They are the conductors of a global symphony of wind and water, sometimes playing a gentle tune, sometimes orchestrating a powerful, even destructive crescendo. The very air we breathe, the rain that falls, the temperatures we feel can all be subtly yet profoundly influenced by this distant Pacific rhythm. It's a testament to the interconnectedness of our planetary systems, where a distant ocean can orchestrate events on faraway lands. In the last few decades, a growing chorus of voices, both scientific and anecdotal, suggests that the strongest of these ENSO events are becoming more frequent, their impacts more pronounced. It is as if the Pacific's heart is beating with a renewed, more vigorous intensity, its ancient rhythm growing louder, more insistent. The destructive consequences have been profoundly felt across our world. Immense floods that reshape landscapes, washing away homes and livelihoods. Parching droughts that wither crops and bring whispers of famine, leaving vast tracts of land thirsty and barren. And tragic mass die-offs of marine life, disrupting the delicate balance of ocean ecosystems, leaving once vibrant underwater worlds silent and desolate. Consider for a moment the poignant tale of the coral reefs. These vibrant living cities beneath the waves, teeming with a kaleidoscope of life, are incredibly sensitive to the temperature of their watery homes. A severe El Niño in 1998, like a sudden fever gripping the ocean, caused an estimated 16% of the world's precious coral reefs to perish. This was not merely a loss of beauty. It was the tragic beginning of a cataclysmic mass bleaching event, a silent, ongoing tragedy that persists even to this day, a testament to the profound, widespread reach of ENSO's influence. The corals, like fragile canaries in the ocean's coal mine, signal a deeper disruption, a warming that touches the very foundations of marine life, turning their vivid hues into ghostly white. This bleaching occurs when the corals, stressed by rising temperatures, expel the tiny colorful algae that live within their tissues and provide them with food. Without these symbiotic partners, the corals begin to starve, leaving behind their pale skeletal structures. It's a stark visual reminder of the ocean's delicate vulnerability to temperature shifts. Indeed, the ENSO cycle is truly global in its reach, a powerful unseen force that will without a doubt impact you, your surroundings, and the greater tapestry of life on Earth. It is a constant reminder of the interconnectedness of our planet, how a shift in the vast Pacific can send ripples through the air across the land and into the very rhythm of our lives. It invites us to consider how intricately woven our world truly is, a delicate balance of forces, some visible, some hidden, all dancing together in a grand cosmic ballet. This is not merely a scientific concept. It is a profound ecological reality, shaping the distribution of rainfall, the intensity of storms, and the very flow of life across continents. From the parched fields of Australia to the flooded riverbanks of Peru, from the thriving fisheries of the Pacific to the struggling coral reefs, ENSO leaves its undeniable signature. As we continue this quiet journey, allowing our thoughts to gently unfurl, we will explore the heart of this fascinating climate cycle. We will ask, what exactly are El Niño and La Niña, these twin forces of ocean and atmosphere? Why are they so intimately linked, two sides of the same powerful coin? And what are their far-reaching global impacts, shaping not just our weather, but the very pulse of life across our magnificent planet? We will approach these questions not with urgency, but with a sense of quiet curiosity, like watching ripples expand slowly on a still pond, seeking to understand the hidden force that created them. This journey into ENSO is a gentle invitation to connect with the deeper rhythms of our world, to listen to the whispers of the wind and the ancient murmurs of the ocean, and to find wonder in the intricate dance of our living Earth. We'll delve into the subtle shifts in ocean temperatures and atmospheric pressures that underpin these phenomena, trying to grasp the immense scale of these planetary interactions. The story of ENSO, as we shall see, is not merely one of scientific data and meteorological patterns. It is a story embedded in human history, woven into the very legends and observations of people who lived centuries ago, long before the tools of modern science could explain the how. It speaks to a universal human experience of seeking patterns, of trying to understand the unpredictable whispers of nature, and of giving names to the powerful forces that shape our existence. This phenomenon, once a mystery to ancient mariners, is now a cornerstone of our understanding of global climate. Yet it retains a certain poetic quality, a sense of its ancient primal power. It reminds us that long before satellites observed ocean temperatures from above human beings, through diligent observation and deep connection to their environment, sensed these profound changes and incorporated them into their worldview. Think of it as a hidden conductor, orchestrating a vast symphony of atmospheric pressure and ocean currents, a performance that repeats itself with a subtle variation each time. The stage for this performance is immense, spanning the vastness of the Pacific, but its audience is truly global. Every continent, every ocean, every living creature feels the echoes of its profound performance. This quiet exploration is an opportunity to tune our senses to these subtle rhythms, to appreciate the delicate balance that sustains life, and to recognize our place within this grand unfolding narrative of Earth's ever-changing climate. We are all part of this story, carried along by its currents, touched by its whispers, and invited to understand its deep rhythmic breath. And as we conclude this introductory chapter, let us hold on to this sense of wonder, this gentle curiosity, as we prepare to peel back the layers of this fascinating planetary secret, one quiet thought at a time. The journey into ENSO promises to reveal not just scientific facts, but a deeper connection to the living, breathing planet beneath our feet. As we continue our gentle journey into the heart of Earth's grand cycles, let us now focus our attention on the specific rhythm known as the El Niño Southern Oscillation, or ENSO. Its very name, El Niño, might conjure images of ancient lore or a whispered folktale, rather than a dry scientific phenomenon, and indeed, you're sensing something truly profound in that intuition. For the story of El Niño began not in a laboratory filled with complex instruments, but on the sun-drenched coasts of South America, among the simple yet observant lives of fishermen. It is a testament to the fact that profound scientific truths often begin as observations in the natural world, long before the tools exist to fully decipher them. Imagine, if you will, the 17th century. The world moved at a slower pace than closely attuned to the rhythms of nature. For generations, humble fishermen along the coasts of Peru and Ecuador had relied on the rich bounty of the Pacific Ocean, their livelihoods intertwined with its generous currents. They knew the predictable patterns of the sea, the regular abundance of fish that came with the cold, nutrient-rich waters welling up from the depths. This cold water, brimming with microscopic life, was their sustenance, their calendar, their very way of life. It was a constant, reliable partner in their daily struggle and their moments of plenty. the ocean provided, and they learned to read its subtle signs, its changes in temperature, and the movements of its teeming life. But sometimes around the festive time of Christmas, a subtle yet unsettling change would arrive. The familiar cool currents would yield to periods of unusually warm water, and with this warmth, the fish, their precious livelihood, would mysteriously vanish or become scarce. It was a disruption to their predictable world, a period of hardship and uncertainty. The vibrant, bustling life of the fishing grounds would grow quiet. The nets would come up empty, and the air would carry a different scent, less briny, more still. This shift was profound for them, hitting at the very core of their existence. These observant souls, deeply connected to the ocean's temperament, named this unwelcome visitor El Niño de Navidad, which tenderly translates to the boy of the nativity, or the Christmas child. It was a recognition of its arrival around the holy season, a gentle, almost reverent acknowledgement of a powerful, mysterious force that appeared to them like a gift, or perhaps a challenge from the heavens. The name itself speaks volumes about a time when humanity viewed nature not merely as a resource, but as a living entity, sometimes benevolent, sometimes enigmatic, worthy of respect, and even a touch of awe. It's a name that lingers, carrying with it the echo of ancient wonder and the deep bond between humans and the sea. For centuries, El Niño remained a local whisper, a tale passed down through generations of fishing communities, a seasonal anomaly tied to their specific coastal experience. It was a phenomenon known by its immediate tangible effects: warmer waters, fewer fish, a disruption to the daily catch. It was a rhythm they endured, a mystery they accepted, perhaps even incorporated into their annual rituals, like a recurring character in their annual story. They adapted, they waited, they hoped for its passing understanding. It as a part of the ocean's great unfolding narrative. It was a localized wisdom, a piece of ancestral knowledge honed by countless observations, passed from parent to child, from elder to apprentice. It wasn't until much, much later, in the late 19th and early 20th centuries, that the first threads of a grander tapestry began to emerge. Scientists, with their burgeoning tools of observation and their relentless curiosity, started to connect a seemingly disconnected scattering of regional events across the vast canvas of our planet. They observed peculiar droughts in distant lands like Australia, where the landscape would turn to dust and the ancient rivers would shrink to mere trickles. They noted unusually heavy rains in certain parts of South America, far from the Peruvian coast, leading to unprecedented floods that reshaped the land. And they began to detect subtle, synchronous shifts in atmospheric pressure across the immense expanse of the Pacific, like a vast unseen breath being held and released. Individually, these seemed like isolated meteorological oddities, perhaps mere coincidences, or the unpredictable whims of local weather. The world from a scientific perspective was still largely seen as a collection of independent weather systems, but the keen minds of early climatologists, like the brilliant British scientist Sir Gilbert Thomas Walker, began to perceive a subtle unseen connection, a shared pulse beating beneath these disparate events. Walker, in his pioneering quest to better understand and predict the strength of the monsoons in India, a crucial element for the lives of millions, began to collect vast amounts of meteorological data from around the globe. In his meticulous search, he stumbled upon a remarkable pattern, a repeating seesaw-like shift in atmospheric pressure that occurred across the equatorial Pacific Ocean. When pressure was high in one part, it was low in another, and vice versa. He called this discovery the Southern Oscillation. It was a profound insight, revealing a large-scale air circulation that had not been documented before, later named the Walker Circulation in his honor. This was the first major scientific breakthrough, revealing a rhythmic breath, far vaster than previously imagined, linking seemingly distant corners of the world through the subtle language of atmospheric pressure. By the mid-20th century, the pieces of this vast jigsaw puzzle finally clicked into place. What had once seemed like isolated irregular occurrences were revealed to be not independent phenomena, but instead interconnected phases of a colossal global cyclical phenomenon. They named this vast overarching dance the El Niño Southern Oscillation, or ENSO. This realization was revolutionary, fundamentally changing our understanding of global climate. It meant that the warm waters off the coast of Peru, observed by those 17th century fishermen, were not just a local peculiarity. They were a symptom, a visible tremor of a much larger global atmospheric and oceanic heart beating across the equatorial Pacific. It was as if the Earth itself was breathing, and these shifts were its deep rhythmic inhalations and exhalations felt in countless subtle ways across the entire world, orchestrating a complex ballet of weather patterns. The ENSO cycle. This vast, slow fluctuation swings between its warm phase, El Niño, and its cool phase, La Niña, with an average interval of about 5 years. However, like a dancer finding their unique rhythm, the cycle can sometimes take a little longer, sometimes a little shorter, anywhere between 2 and 7 years. This variability, this slight unpredictability, adds to its mysterious charm. It reminds us that nature, even in its grandest patterns, is not always rigidly precise, but possesses a graceful, organic flexibility. It is not a fixed clockwork, but a living, breathing system with its own subtle nuances and unexpected pauses. This natural variation in duration means that predicting the exact onset or length of an ENSO event remains a delicate art, a challenge that keeps scientists humbly engaged with the planet's powerful, ever-changing mood. For decades now, with the advent of advanced satellites, ocean buoys, and sophisticated computer models, we have been diligently tracking these cycles, meticulously recording their subtle shifts and powerful manifestations. We monitor the surface temperatures of the Pacific with thermal sensors orbiting hundreds of miles above like watchful eyes from the heavens. We deploy networks of buoys that bob gently on the ocean's surface, constantly gathering data on temperature and currents acting as silent sentinels in the vast blue expanse. And we feed this torrent of information into powerful supercomputers, creating intricate models that simulate the complex interplay of forces. Yet, it is a humbling thought that these cycles have been occurring for far, far longer than our brief period of scientific observation. They are ancient, primal rhythms etched into the very history of our planet, influencing life and climate long before humanity even walked the Earth. Long before our species even began to gaze up at the stars and wonder about the grand patterns of the cosmos. Our scientific understanding is merely a recent chapter in a story that spans eons, a story written in the deep layers of oceanic sediment and the faint whispers of ancient winds. To truly appreciate the profound significance of the El Niño Southern Oscillation, and to understand why it occurs, we must first gently journey into the heart of the Pacific Ocean and observe what happens under what we consider normal conditions. Imagine this vast expanse of water, stretching thousands of miles as a colossal stage where the initial movements of this grand climate dance unfold. This normal state is not static, but a dynamic equilibrium, a delicate balance of forces that, when undisturbed, allows for a vibrant and predictable pattern of life and weather. It is the baseline, the quiet hum against which the dramatic melodies of El Niño and La Niña are played. Under these normal or neutral conditions, a consistent, powerful force is at play. The winds blow steadily along the equator from east to west. These are not just any winds. They are the famous trade winds. Their steady westward push across the ocean is a magnificent product of the Earth's majestic rotation, a phenomenon we call the Coriolis effect. These winds are so consistent, so reliable, that for centuries mariners navigated the globe by harnessing their predictable strength, their sails filled by this constant eastward flow. The name itself, trade winds, speaks to their historical importance in facilitating global commerce, silently guiding ships across vast distances. Let us pause for a moment to ponder the elegant mechanics of this effect, for it is a key player in shaping Earth's atmospheric ballet. Here is a delightful thought to carry with you. If our planet were not spinning, if it were a still unmoving sphere, the air would circulate in a far simpler fashion. It would move directly from the high-pressure colder poles towards the warmer low-pressure region of the equator, a simple north to south flow like water seeking its lowest level. But our Earth, this vibrant spinning top, adds a beautiful twist to this elegant simplicity. As it happens, air does indeed circulate away from the poles, drawn by the warmer lower pressure near the equator. But as this air approaches the equator, it doesn't travel in a straight line. Oh no, the Earth's rotation bends its path, deflecting it, transforming what would be a simple straight current into a magnificent swirling band. This deflection creates circumferential bands of wind curving away from their initial north-south trajectory. In the northern hemisphere, air tends to deflect to the southwest, and in the southern hemisphere, it deflects to the northwest. This magnificent channel of westward-moving air, flowing with remarkable consistency, is what we affectionately call the trade winds. And it turns out these winds are not just charming historical relics, important only if you were a swashbuckling pirate living in the 18th century, navigating your ship across vast oceans by harnessing their predictable strength. Their true importance for our story of Enso lies in their profound effect on the ocean itself, as these trade winds blow steadily and persistently westward across the immense expanse of the Pacific Ocean. They perform a colossal yet delicate task. They drag the warm surface water from the coasts of South America, pulling it patiently, inexorably, towards the distant shores of Asia. Imagine a giant invisible hand gently sweeping the surface of a vast bathtub, pushing the warmer water before it. This continuous push causes the sea level in the Western Pacific near Asia to be slightly higher by as much as half a meter than in the Eastern Pacific near South America. A subtle tilt across the vast ocean surface, and as this warm water is pulled westward, something equally remarkable, a true wonder of oceanic dynamics, occurs beneath it. Colder water rich in vital nutrients is drawn up from the depths to replace the displaced warm water. This phenomenon is known as upwelling. Think of it as the ocean's circulatory system, drawing deep, cool, life-sustaining blood to the surface. It's like a vast, unseen pump, constantly bringing fresh, invigorating waters from the dark, cold abysses to the sunlit surface. This upwelled cold water is a veritable liquid treasure. It is teeming with nutrients that act as a feast for phytoplankton, the microscopic plant-like organisms that form the very base of the marine food web. These tiny green specks, invisible to the naked eye, but numbering in the trillions, flourish in the cool, nutrient-rich embrace of the upwelled water. They are the primary producers, converting sunlight into energy, much like plants on land, and these phytoplankton, in turn, support vast and vibrant ecosystems of fish, from the smallest anchovies to the largest tuna and everything that feeds off them. From krill to whales, from small sardines to giant tuna, and ultimately to the birds that swoop down from the sky and the human communities that rely on the ocean's bounty. It is a chain of life intricate and magnificent, all stemming from the upwelling's nurturing touch, a testament to the ocean's remarkable productivity when its natural rhythms are allowed to flourish. This is why the waters off Peru normally are some of the most fertile fishing grounds in the world, supporting enormous populations of marine life. So as you can imagine, a sudden powerful shock to this finely tuned system. This delicate balance of wind and water, this flourishing chain of life would have a major domino effect on marine life and by extension, on the countless beings including ourselves who depend on the ocean's health. It is like disrupting the very foundation of a grand thriving city or cutting the main artery of a vast living organism. The consequences would ripple outwards, touching every corner of the vast oceanic realm, and then carried by atmospheric currents, spread far beyond affecting distant lands and lives in profound ways. The food web so intricately balanced would begin to unravel. This gentle rhythm, this predictable flow of warm water westward, and the upwelling of cold, nutrient-rich water in the east, represents what normal conditions look like in the Pacific Ocean. It is a state of equilibrium, a stable baseline against which we can understand the grand deviations that occur during the phases of ENSO. It is the quiet, steady breath of the ocean, a breath that sustains so much life, a breath that forms the very foundation of our exploration into its profound global impacts. And in our next gentle musing, we will delve into what happens when this normal, predictable breath is subtly yet powerfully disrupted, ushering in the phase known as El Niño. Now let us turn our attention to the great disruption, the subtle shift in the Pacific's vast normal rhythm that marks the arrival of El Niño. Imagine the steady westward flowing trade winds, those faithful atmospheric currents we just discussed, as the diligent guardians of the ocean's balance. During an El Niño event, these winds, for reasons not yet fully understood by our science, perhaps a whispered cosmic breath or a complex interplay of atmospheric pressures, begin to falter. They weaken, they slacken, their steady push across the vast Pacific becomes less insistent, less forceful. It is like the breath of a giant, becoming shallower, less powerful, as these trade winds slow down the colossal work they usually perform, dragging the warm surface water towards Asia and allowing the cool, nutrient-rich water to well up in the east is profoundly altered. Instead of being swept westward, the warm water that normally accumulates near the coasts of Asia begins to build up, gently spreading back towards the central and eastern Pacific, particularly near the coastal Americas. Think of it as a vast warm blanket slowly unfurling itself and drifting eastward across the ocean surface. This accumulation of warm water means that the essential phenomenon of upwelling, that vital rising of cold, nutrient-rich water from the deep, is significantly reduced, sometimes even temporarily stopped. The ocean's great circulatory system, its powerful invisible pump, slows its rhythm, and less of that life-giving cold water reaches the sunlit surface. This in turn creates a colossal zone of unusually warm air and water, further east in the Pacific, stretching for thousands of miles. The very atmosphere above this warmer water responds, becoming warmer and more humid, rising in great unseen plumes. This profound shift in the ocean's temperature has a cascade of effects, much like a single quiet pebble dropped into a vast still pond, sending ripples far and wide. With less upwelling, the fish, those creatures of habit and sustenance who rely so intimately on the phytoplankton, fed by the cold, nutrient-rich waters, find their accustomed feast dwindling. They must then make a stark choice, migrate to distant, cooler waters where food is still abundant, or face a slow, silent struggle for survival, which for many sadly means to perish. This impacts not just the marine life itself, but also the coastal communities whose lives and livelihoods are intertwined with the ocean's bounty, transforming once bustling fishing harbors into quiet, anxious places. The whispers of hardship begin to ripple through human settlements, echoing the struggles of the marine world. But the influence of this vast, warm blanket in the Pacific does not stop at the ocean's surface. It reaches into the very skies, profoundly altering global atmospheric patterns. The mighty Pacific jet stream, that river of fast-moving air that usually crosses North America along a predictable path, is pushed southward from where it normally occurs. Imagine this powerful, invisible river in the sky, suddenly forced to shift its course like a grand, meandering serpent. As a direct consequence of this southward shift, the weather patterns across vast stretches of land are dramatically reorchestrated. The northern United States and Canada, typically accustomed to more varied winters, tend to become unusually warmer and drier during an El Niño. The usual patterns of snowfall might diminish, and the air might carry an unexpected mildness. Conversely, the Gulf Coast of the United States and significant parts of coastal South America, particularly nations like Peru and Ecuador, experience a profound reversal. They tend to become much wetter, receiving far more rainfall than is typical for their seasons. In Peru and Ecuador, for instance, their wettest months usually occur between April and October. But during more severe El Niño years, the rain that descends upon these regions can be truly catastrophic, transforming landscapes and altering lives in profound ways. These are not merely heavy showers. They are deluges, vast curtains of water that can overwhelm natural and human systems. Consider the poignant and devastating severe El Niño of 1997 to 1998. During this powerful event, torrents of devastating floods bombarded Peru. Rivers swelled beyond recognition, their waters roaring through towns and villages. Bridges, those steadfast links across divides, collapsed under the relentless force of the water severing connections and leaving communities isolated. Entire shanty towns, fragile collections of homes built on precarious land, were buried under a meter-thick layer of thick, heavy mud, leaving behind only echoes of their existence. In total, 250,000 people were displaced from their homes, forced to abandon everything familiar. Becoming climate refugees in their own land, their lives irrevocably altered by the sheer power of the ocean's shift. The region of Tumbes, normally a parched, arid landscape, received an unbelievable 16 times its average annual rainfall, a transformation from desert to deluge, a stark illustration of El Niño's capacity for extreme reorchestration of weather patterns. It was as if the sky itself had wept relentlessly, reshaping the very contours of the earth. But the story of El Niño's influence reaches far beyond the Americas. Its subtle yet powerful hand sets off a complex series of effects that significantly alters weather worldwide, a global ripple that touches distant continents and influences the lives of billions. The increased rainfall in South America, a consequence of the shifted jet stream, typically coincides with a pronounced period of drought in South Asia and Australia. Imagine the balance, the exchange, the deep connection. One side of the world receives an abundance of water while another is parched. In India, a nation profoundly reliant on the annual monsoon rains for its agriculture and sustenance, severe famines have been tragically recorded during El Niño years. The delay or weakening of the monsoon season, that life-giving breath of rain, can lead to widespread crop failures, threatening the food security of vast populations. The land, usually verdant, turns brittle and dusty, the promise of harvest withers, and the whispers of hunger grow louder. It is a reminder of humanity's intimate, often precarious connection to the rhythms of the climate. And in Australia, a land known for its vast expanses of grassland and its unique, often fragile ecosystems, a delay in its monsoon season can lead to massively destructive bushfires. These fires, fueled by dry vegetation and often exacerbated by intense heat, can sweep across the landscape with terrifying speed and ferocity. Due to its unique geography and climate, Australia's bushfires are some of the most destructive on Earth, leaving behind vast charred landscapes and profound ecological devastation. There are already profound concerns even now about a potential event that could occur late in 2023 as the echoes of past infernos linger in collective memory. Leaders and communities, understandably, are worried, particularly given recent warming trends that seem to amplify the ferocity of these natural disasters. You may recall with a shudder that in 2020, even in a non-El Niño year, bushfires wrought nightmarishly apocalyptic scenes across Australia. 50 million acres of land were charred to a crisp, an area larger than many European countries. The skies glowed an eerie orange, and the air was thick with smoke, creating scenes that truly felt like the end of days. Australia in many ways is a literal tinderbox, and the looming prospect of El Niño hovers over it like a proverbial flamethrower, threatening to ignite its dry landscapes. So, local officials and communities are wise to prepare for the worst, learning from the harsh lessons of the past, seeking to build resilience against this powerful, unpredictable force. On a global scale, the average surface temperature during an El Niño event rises, albeit subtly, by about 0.1 degrees Celsius. This might sound like a small number, a mere whisper of warmth. But on a planetary scale, such a shift can have profound implications, influencing the delicate balance of ecosystems and atmospheric dynamics. It's like the gentle turning of a vast thermostat, imperceptible to our individual touch, yet capable of shifting the entire room's comfort. It's important to remember, however, that not all El Niño events are severe. Just as a river can flow gently or rage furiously, some El Niños can be rather mild, bringing only subtle shifts in weather patterns. This is something crucial to keep in mind before one might be tempted to hit the panic button, for the natural world is full of nuanced expressions. The average El Niño lasts from 9 to 12 months, a significant portion of a year, allowing its effects to unfold gradually. But on rare occasions, these events have extended for years, stretching their influence across multiple seasons, leaving a deeper, more prolonged imprint on the planet. The world's climate, as we are beginning to appreciate, is a pretty complex system responding to a myriad of inputs and feedback loops, like a colossal interwoven tapestry of forces. Thus, the effects of El Niño are best understood not in isolation, but as relative to what the baseline conditions would ordinarily be. This is why no two El Niño years are exactly alike. Each event unfolds with its own unique character, shaped by the prevailing conditions and the subtle interplay of countless variables. It is a dance where the steps are familiar, but the precise choreography is always a little different, always holding a hint of surprise, a reminder of nature's endless variability. This nuance is crucial to our understanding, inviting us to observe and learn rather than to simply categorize. In our continuous gentle exploration, we have now touched upon the warm phase of the El Niño Southern Oscillation, witnessing its profound ability to reshape weather patterns and impact life across the globe. But the story of ENSO is a dual narrative, a powerful duality. For every warm embrace of El Niño, there is a cool counterpart, a mirror image that brings its own distinct set of influences. In our next quiet contemplation, we will turn our attention to this other side of the coin, to the refreshing, intensified normalcy that is La Niña. It is a testament to the beautiful cyclical nature of our planet, where balance is eventually restored even after the grandest of disruptions. We have journeyed through the gentle disruption of El Niño, witnessing how the warming of the vast Pacific can reorchestrate weather patterns across the globe. Now let us turn our gaze to the opposite side of this profound climate oscillation, to its cool counterpart, a phenomenon known as La Niña. If El Niño is a warm event, a spreading blanket of heat across the ocean, then La Niña is in essence a cool one. However, like a river finding its unique path, some regions do experience a gentle warming during La Niña, reminding us that nature's tapestry is woven with countless nuanced threads. As I mentioned earlier, El Niño occurs when the equatorial trade winds, those faithful currents of air that normally push warm water westward, begin to slacken, to lose their insistent force. But during La Niña, the very opposite occurs. These trade winds become even stronger, more vigorous, more determined in their westward push. Imagine them as a great unseen hand sweeping across the ocean's surface with renewed strength, clearing the way. Think of El Niño as a subtle disruption of normal conditions, a pause in the predictable flow. Then consider La Niña as normal plus, an intensification of those very conditions we described earlier as typical for the Pacific. It's as if the ocean's steady heartbeat, instead of faltering, grows even more robust, its rhythm more pronounced. With these invigorated trade winds blowing even more warm water from the coastal Americas towards Asia, a powerful consequence unfolds in the eastern Pacific. The upwelling of cold, nutrient-rich water, which might have diminished during El Niño, now becomes even more pronounced, more vigorous. Vast quantities of cold, deep-sea water surge to the surface near the coasts of the Americas, particularly off Peru and Ecuador. This is like the ocean's circulatory system kicking into a higher gear, pumping an even greater abundance of life-giving water from its cool, dark depths. For fisheries, this can herald a veritable feeding frenzy. The explosion of phytoplankton, nourished by the super-rich upwelled water, creates an unparalleled feast for the entire marine food web. If you like salmon, for instance, well, you're in luck during La Niña cold water species. Like salmon, which normally prefer specific cooler habitats, will venture into typically warmer waters, exploring new territories where they can't ordinarily survive, drawn by the incredible abundance of food. The same is also true for squid, those fascinating swift creatures of the deep, in case you prefer calamari. Fishermen along these coasts often experience periods of immense bounty, a direct contrast to the lean times of El Niño, a testament to the ocean's remarkable capacity for renewal and generosity when the conditions are just right. Meanwhile, in Asia, where the strong trade winds have now pushed an even greater influx of warm equatorial water, the conditions become remarkably wet. This is the precise opposite of the parching drought experienced during El Niño. Vast plumes of warm, moist air rise into the atmosphere, leading to increased cloud formation and abundant rainfall. This can cause a significant spike in tropical cyclones, those powerful swirling storms that draw their energy from warm ocean waters. The Western Pacific and regions like Southeast Asia can experience intensified monsoon seasons and more frequent powerful storms, a deluge of nature's bounty, sometimes overwhelming. In North America, the shift is equally profound, though with distinct regional variations. The mighty jet stream, that river of air in the sky, is pushed even further north than its usual path during La Niña. Imagine it shifting its course, guiding atmospheric currents in a new, more northerly trajectory. This northward displacement has a specific consequence. It typically causes prolonged periods of drought in the southwestern United States, a region already prone to aridity, intensifying the dryness and straining water resources. Conversely, the Pacific Northwest, further north, experiences abundant rains, soaking the landscape and filling its rivers and reservoirs. Consider the stark reality of 2022, when a prolonged La Niña exacerbated a mega drought in the southwestern United States, making it the worst in an astonishing 1,200 years. This wasn't just a dry spell. It was an event of historical proportions, leaving landscapes parched and water sources critically low. Just look at images of Lake Mead, for example, the colossal reservoir that feeds the Hoover Dam, a vital lifeline for millions. That light area, often referred to as the bathtub ring, ordinarily covered by water, now stands starkly exposed, a stark visual testament to the severity of the drought and the profound impact of La Niña's influence. It's a sobering reminder of how interconnected our climate systems are with our very survival, particularly in regions dependent on snowmelt and rainfall. Now, with all this talk of trade winds and jet streams, you might be wondering how La Niña affects hurricane season, those powerful swirling storms that command so much attention. Well, depending on where you live, the news is either a gentle relief or a cause for heightened vigilance. The Atlantic often experiences a much more severe hurricane season during La Niña. The shift in the jet stream to the north creates an environment of greater atmospheric instability in the southern Atlantic, promoting conditions conducive to the formation and intensification of hurricanes. This can mean more storms and potentially stronger ones, making coastal communities along the Atlantic seaboard more vulnerable to the powerful forces of wind and water. It's a time when vigilance is paramount and preparedness becomes a shared responsibility. But the Pacific Basin actually sees fewer hurricanes during La Niña, a fascinating counterpoint and a clear sign of how drastically different these regional effects can be. While the Atlantic hums with increased storm activity, the Pacific experiences a relative quiet, a subtle shift in the balance of atmospheric energy. Just don't get too complacent, Pacific dwellers. El Niño has the opposite effect, ushering in more Pacific hurricanes, reminding us that the balance is always in flux, always subject to the grand oscillation. Meanwhile, in Pacific coastal South America during La Niña, you won't see the warm Christmas-time waters that once prompted fishermen to dub it El Niño de Navidad. Indeed, there's a reason why fishermen once called La Niña el Viejo, or the Old Man, a subtle acknowledgement of its contrast to the Christmas child and its typical association with cooler, more stable conditions, almost a return to the established ways. During La Niña, The weather in Peru and Chile turns colder and drier, sometimes producing severe periods of drought, once again mirroring the conditions of abundance in other regions. Brazil's north, on the other hand, becomes remarkably wet during the months from December to February, transforming landscapes and influencing agricultural cycles. And the lowlands of Bolivia, often susceptible to the whims of the weather, can receive catastrophic flooding during La Niña, turning vast plains into temporary lakes, a profound testament to the power of the cycle. In Africa, the conditions during La Niña years are basically the reverse of what they are during El Niño. East Africa tends to experience drier than average conditions, intensifying challenges for agriculture and water security, whereas the South tends to be wetter than average, bringing welcome rains to some areas while potentially causing localized flooding in others. It's a complex mosaic of effects, reminding us that a single global phenomenon can manifest in a multitude of ways across diverse landscapes. So where are we now in this grand unfolding story of the ENSO cycle? As of the making of this video, and allowing for the gentle passage of time in our contemplation, the National Oceanic and Atmospheric Administration, often referred to as NOAA, has declared an end to a lengthy, powerful 1.5-year La Niña event. This prolonged cool phase had left its distinct imprint on global weather patterns, shaping the experiences of countless communities. NOAA reached this conclusion based on meticulous scientific measurements, specifically by observing the difference in surface atmospheric pressure in the western and eastern Pacific. This metric is known as the Equatorial Southern Oscillation Index, a vital pulse reading of the vast Pacific's atmospheric heart. The last reading of it was just 0.1, a subtle whisper of a number down significantly. From 1 a year ago, meaning conditions have returned pretty much to what we consider normal. It's like the patient's fever has broken and their temperature has stabilized, albeit for a fleeting moment. It's still early to say anything definitive, for the climate is a dynamic living system, but there are already gentle indications, subtle whispers in the atmospheric data, that an El Niño will occur later in 2023. Currently, NOAA is forecasting a 60% chance that El Niño sets in by autumn, a quiet murmur of change on the horizon. This would have major ramifications, of course, reshaping weather patterns for the coming year. India, a nation keenly attuned to the rhythms of the monsoon, is already warning its citizens of potential drought conditions, preparing for the possibility of altered rainfall patterns that could impact its vital agricultural sector. There's another subtle, almost poetic reason to expect an El Niño in 2023, albeit based purely on past experience and the grand rhythmic memory of the Earth. Since we started tracking ENSO in the 1950s, the cycle has never allowed for more than a 4-year period without an El Niño event. So if there isn't one in 2023, it would mark the first 5-year gap without one, breaking a historical pattern that has held true for decades. It's like a long-playing record where the melody repeats with comforting regularity, and a significant pause would be an anomaly in its familiar tune. This observation isn't a prediction with certainty, but rather a whisper from the Earth's past, a gentle hint of its enduring cyclical nature. For me, this is an excellent example of how studying climate cycles, even those as vast and complex as ENSO, can help us prepare and foster human survival. Not just on this world, but potentially on other worlds too. This grand perspective, this ability to look beyond our immediate horizon, is deeply inspiring. One of the truly fascinating aspects of ENSO is the profound level of insight we gain from it into Earth's complex climate systems. It's like a master key, unlocking deeper understandings of how our planet functions as a whole. Understanding the intricate interconnectivity of our own planet's climate, how every current and wind whispers to another, will be absolutely crucial if we ever dare to dream of settling on other planets or even embarking on the monumental task of terraforming them. If humanity eventually undertakes the huge imaginative task of terraforming Mars, transforming its cold, arid landscape into a lush, breathable world, or Venus reshaping its searing, toxic atmosphere. Or perhaps even an exoplanet, a distant world in some other part of the Milky Way galaxy. Our success will likely depend entirely on our ability to understand the various inputs and feedback loops that intricately interlink climate systems and biospheres. It's a grand vision, a testament to humanity's boundless curiosity and ingenuity. That day may seem far off, a distant star in our collective future, but it isn't too early to start dreaming, to allow our imaginations to gently wander into those vast possibilities. The lessons we learn from the subtle dance of Enso on Earth are profound. They teach us about atmospheric dynamics, ocean currents, energy transfer, and the delicate thresholds that maintain planetary habitability. These are not merely academic lessons. They are blueprints for a potential future amongst the stars. So there we have it, a quiet, in-depth primer on the El Niño Southern Oscillation. The ENSO can be a very destructive cycle for our planet's animal and human populations, bringing hardship and challenge. But life is nothing if not adaptable, resilient, and resourceful. More likely than not, 2023 will add another piece to the growing body of documentation about these powerful events, enriching our understanding layer by layer, like sediment building up on the ocean floor. As we conclude this contemplation, I invite you to consider: how has El Niño or La Niña affected you, perhaps without you even knowing it? Have you noticed any interesting, subtle changes in your part of the world? Changes in rainfall temperature, or even the subtle mood of nature? I'd love to hear about it in the comments as we continue this shared journey of discovery, learning from each other's experiences and observations. The story of Earth's climate is a vast, ongoing narrative, and each of us is a quiet observer, a participant in its unfolding. As the gentle hum of the El Niño Southern Oscillation slowly fades from our quiet contemplation, let us now allow our minds to drift even further into the vastness of cosmic time. We turn our attention from the rhythmic breath of the oceans to a grander, slower ballet, the intricate celestial dance that our Earth performs as it journeys through the solar system. This is a story of profound ancient rhythms, subtly orchestrating the very climate of our world over timescales that dwarf our fleeting human lives. Winter is coming, uttered Eddard Stark in the popular television series Game of Thrones. When he spoke those famous words, it was more than just a simple pronouncement of the normal passing of the seasons. In the fantasy realm of Westeros, winter was a formidable entity, a problem of immense scale that could potentially last for years, even up to a decade. Crops would wither, the weather would turn brutally cold, and the very survival of civilization would be tested. The arrival of winter was the harbinger of an era of profound hardship, a challenge that reshaped lives and destinies. Of course, while Westeros is pure fantasy, a tapestry woven from imagination seasons that last for years on end are not limited to fictional stories. We experience them in a profound and subtle sense right here on Earth. Our planet is constantly influenced by various cycles, some short and familiar, others vast and imperceptible to our daily lives. When these grand ancient cycles are in a delicate balance, working in harmony, we experience a period of relative stability, a temperate calm. It's like a complex musical piece where all the instruments play together in a harmonious chord. It's worth noting, though, that this harmonious balance will not last forever. In our planet's future, winter is coming too, a winter of a much grander scale than we can easily imagine. So what are these magnificent ancient cycles? How can better understanding them help us prepare for our distant future, perhaps even for winters that span thousands of years? Join me today in gently exploring these different rhythms that affect our planet's weather and warmth, unveiling the hidden choreography of our cosmic home. To begin, we should probably ask a simple yet profound question that many of us believe we already know the answer to: what causes the seasons that we are so familiar with, the cyclical dance of spring, summer, autumn, and winter? You may well already know the answer to this question, or at least a part of it. But as it will provide the quiet starting point for what comes later, a foundation for understanding the deeper rhythms it's worth reviewing. Besides, this question is not entirely straightforward. For depending on where you are on the planet, you may not actually experience seasons in the way many of us do. Near the equator, for example, the concept of 4 distinct seasons can blur into a more continuous pattern of warmth and rainfall, a subtle reminder of Earth's diverse climates. Generally speaking, the seasons as we know them are caused as a direct result of our planet's axial tilt. Imagine Earth not as a perfectly upright spinning top, but rather as one tilted gently on its side, leaning at an angle as it orbits the Sun. Because our planet rotates at this tilted angle as it gracefully orbits the Sun, one hemisphere, either the northern or the southern, will point more directly towards the Sun during a part of the year, while the other will point subtly away. Naturally, the hemispheres that are pointed more directly towards the Sun receive more direct sunlight, absorbing more of its warmth and consequently become much warmer. This brings forth the vibrancy of summer. Conversely, the hemisphere that is pointed away from the Sun receives more oblique sunlight, scattering its energy over a wider area, and thus becomes colder. This ushers in the hush and chill of winter. This constant, predictable dance of tilt and orbit creates our regular seasons of summer and winter, a beautiful interplay of light and shadow, warmth and cold. This effect, the contrast between summer's warmth and winter's chill, becomes stronger the higher up or lower down the planet you go closer to the poles. Consider for a moment the small Norwegian town of Tromsø. Situated far to the north, well above the Arctic Circle, Tromsø experiences the tilt of the Earth in a truly dramatic fashion. Because of its higher latitude, Tromsø isn't just pointed more towards the Sun during summer. The tilt of the Earth is such that from its unique perspective, the Sun never fully sets for months in summer. Imagine the continuous glow of the midnight sun painting the sky with an ethereal light, even at the darkest hours of the night. This continuous daylight bathes the landscape in warmth and fosters intense growth. Conversely, during winter, the tilt of the Earth means that for a few months, the Sun never rises above the horizon in Tromsø. The world is plunged into the profound stillness of the polar night, a long dark period of deep cold. Naturally, this produces quite the seasonal variance, a dramatic swing between perpetual daylight and endless twilight, between relative warmth and intense cold. It is a striking example of how the Earth's tilt orchestrates such profound differences in climate across its surface, creating unique and extreme environments. However, this effect lessens dramatically the closer you get to the equator. There, the tilt of the Earth doesn't really change how close or far away from the Sun the area is throughout the year. The Sun's rays strike the equator almost directly all year long, and as such, the Earth in these tropical regions doesn't notice much temperature variation. It's all just a question of how close you are to the Sun's most direct embrace, and at the equator, that embrace is constant and warm. This explains why many equatorial regions experience seasons, not of temperature, but of rainfall, wet and dry seasons, a different kind of rhythm, but a rhythm nonetheless. Now let us introduce a layer of profound wonder to our understanding. Did you know that the tilt of the Earth isn't static, isn't fixed in place like an unchanging statue? Nor is it the only thing about the planet's grand orbit that influences how warm or cold we are, or how the seasons unfold over vast stretches of time. Imagine for a second the simplified model. You might be familiar with our Earth orbiting the Sun in a nice, perfect circle, flat to the plane of the solar system, like a marble rolling smoothly on a glass table. In this idealized model, we circle the Sun because of the Sun's immense gravity, a single dominant force. This model, while a good starting point, is in reality too basic, too simple to capture the exquisite complexity of our solar system. In truth, the Sun, while undeniably the largest and most powerful gravitational anchor, is not the only source of gravity gently pulling at us. Many of the other planets, those distant wanderers in our cosmic neighborhood, also exert their subtle gravitational tugs and targets on Earth. Consider the colossal presence of Jupiter, the magnificent gas giant with a mass 318 times the size of our own planet. Its immense gravity, though distant, has a profound influence. Or Saturn, that ringed jewel of the solar system, 95 times our mass. Even Venus and Mars, our closer neighbors, exert their gentle pulls. And we, in turn, exert our own tiny reciprocal pull on them. It is a cosmic dance of mutual attraction, a silent, continuous conversation of gravitational forces across the vastness of space. As these planets, each magnificent in its own right, rotate at different speeds around the Sun at varying distances and orbital periods, this constant pulling and releasing creates a delicate, intricate dance. It is far more complicated than a simple, perfect circle, more akin to a complex, multi-layered choreography. This interplay of increasing and lessening gravity has many different profound effects on our Earth. It subtly influences our angle of tilt, the very shape of our orbit, and even the plane in which our orbit occurs. It's like a vast, unseen hand gently nudging our planet, causing it to subtly wobble, stretch its path, and bob up and down. Broadly speaking, these variables influenced by the gravitational whispers of our cosmic neighbors have stabilized into magnificent, predictable cycles themselves. These grand cycles were first described effectively with remarkable foresight and mathematical precision by the Serbian geophysicist and astronomer Milutin Milankovic in 1920. And thus, they were rightfully named Milankovic cycles in his honor, a lasting tribute to his profound insights into the long-term rhythms of Earth's climate. These cycles, unfolding over immense timescales, are the true conductors of Earth's deepest climate changes, shaping the planet's warmth and cold across millennia. The first such cycle I wish for us to gently explore is the changing shape of our orbit. Imagine our Earth's path around the Sun not as a perfectly round circle, but as an ellipse, like a slightly squashed circle. Over the course of a colossal 100,000-year period, this elliptical shape subtly changes, becoming more pronounced, and then gradually returning to a more circular form. It's like a great cosmic rubber band, being gently stretched and then allowed to relax. Naturally, if our orbit is closer to that of a perfect circle, our distance from the Sun remains relatively consistent throughout the year. This means we receive about the same amount of sunlight all year round, leading to more stable, less extreme seasons globally. It's like living in a perfectly temperate, unchanging garden. However, once our orbit becomes more elliptical, there are distinct parts of the year when we are further from the Sun and thus receive less direct sunlight and warmth, making those periods colder. And conversely, there are parts where we are closer to the Sun, receiving more intense sunlight and warmth, making those periods warmer. This subtle stretching of our orbit introduces a profound seasonal variation, not on a daily or yearly scale, but over immense spans of time. As it happens, the perihelion of the Earth's orbit, the point where we are closest to the Sun, occurs roughly on January 3rd, and the aphelion, the point where we are furthest away, happens roughly on July 4th. For those of us living in the Northern Hemisphere, January is deep winter, while July is the heart of summer. So for my hemisphere, the fact that we are closest to the Sun in January means our winters are subtly warmer, a gentle tempering of the chill. And when we are furthest in July, our summers are subtly milder, a slight relief from the intense heat. Right now, we are in a phase where the cycle of the Earth's orbit is more circular than it is elliptical. Yet even in this relatively circular phase, we still experience a noticeable 7% difference in the amount of sunlight we receive in January compared to July. This might seem like a small percentage, a mere whisper of difference, but its cumulative effect can be profound. This subtle sunlight difference means that my Northern Hemisphere's winters are indeed warmer, while our summers are milder. It's a natural form of climate moderation. In the Southern Hemisphere, however, the reverse is true. Because they are experiencing summer during this warmer phase, January, their summers become even warmer, potentially more intense, and their winters, July, become colder. This is just at this current stage of the 100,000-year Milankovitch cycle. As the Earth's orbit gradually becomes more elliptical over thousands of years, that 7% sunlight difference can dramatically increase, turning into a staggering 23% difference between perihelion and aphelion. That is quite significant, a powerful pendulum swing of warmth and cold across the globe. You might think, gazing at this orbital dance, that this seems overall a little unfair on the southern hemisphere. The northern hemisphere appears to benefit from this cycle, stabilizing its seasons, making them less extreme, while the cycle seems to make the southern hemisphere's seasons more extreme, hotter in summer, colder in winter. But do not worry, for, as with all grand ballets, another cycle is at play, a second elegant dancer, stepping onto the stage to bring things full circle, ensuring a long-term balance. This current seasonal rotation, where the northern hemisphere benefits from milder seasons, happens because the Earth's tilt is consistent as it orbits. Except, as we've already hinted, it isn't truly consistent. Little by little, over immense stretches of time, the angle at which the Earth's axis is rotating, its very pointing in space, is gently changing too. Imagine our planet as a spinning top whose axis is slowly drawing a tiny circle on the celestial sphere above it, like a crayon patiently outlining a vast unseen pattern. This grand slow wobble, known as axial precession, completes one full circle in a cycle that lasts a colossal 26,000 years. One remarkable upshot of this slow wobble is that, while our axis is currently pointing at the North Star or Polaris, that steadfast beacon in our night sky, this will eventually no longer be the case. Over time, as the axis completes its grand circle, it will point at different stars, becoming the new North Star for future generations, before eventually circling back to point at Polaris again millennia from now. It is a profound reminder of the fleeting nature of even celestial constants. The other, perhaps more immediately relevant upshot of this axial precession is that in approximately 13,000 years, the northern hemisphere will be having its summer in January and its winter in July. In that distant future, the southern hemisphere will be the one with the possibility of a white Christmas, a profound reversal of our current seasonal experience. So then it will be us in the northern hemisphere experiencing a more profound seasonal variation, harsher winters and hotter summers, while the southern hemisphere enjoys the moderating influence. It is a grand cosmic exchange, a testament to the long-term balance of forces in our solar system, ensuring that neither hemisphere perpetually holds the advantage or the extreme. The Earth's long memory, etched in these cycles, always seeks a subtle equilibrium. We have gently explored the familiar rhythms of day and night, the annual dance of the seasons, and even the subtle cosmic sway that shifts our Earth's tilt and orbital shape over vast stretches of time. Now let us delve into an even grander, more profound mystery, the Milankovitch cycles that create winters of unimaginable duration periods, not of mere months or years, but of thousands of years. Or to speak more accurately, there are Milankovitch cycles that help cause ice ages. The precise mechanisms by which ice ages come and go remain one of Earth's great unsolved puzzles, a profound mystery that science continues to unravel. There are numerous theories, each a thread in a complex tapestry, seeking to explain these monumental shifts in our planet's climate. However, it must be noted that some of the colossal 100,000-year spans of ice ages align with remarkable precision with the 100,000-year Milankovitch cycles. It's a correlation too striking to ignore, suggesting a deep fundamental connection. Consider, for instance, a cycle whereby the plane on which the Earth rotates around the Sun, its orbital inclination subtly rises and falls over the course of 100,000 years. Imagine our solar system not as a perfectly flat disk, but as a vast invisible stage where the planets occasionally bob up and down slightly out of alignment with each other. This change in its orbital inclination does not at first glance obviously explain why it is. that the Earth would be getting colder or warmer. After all, the Earth is still roughly the same distance from the Sun. The amount of direct sunlight received might not seem dramatically altered by this subtle bobbing. However, this cycle aligns so perfectly with the time periods when monumental ice ages were occurring over the last 800,000 years that scientists conclude there must be a profound, yet perhaps unseen connection. It's like finding two gears of vastly different sizes turning in perfect synchronicity. There must be an intricate hidden mechanism linking them. Perhaps during certain inclinations, our solar system passes through denser patches of cosmic dust lying in the plane of Earth's orbit. This invisible veil of dust, though imperceptible to our eyes, could subtly block out some sunlight when we are at one inclination, casting a faint cosmic shadow upon our world. But then it might not be in the way when we are at another inclination, allowing more warmth to reach us. This delicate interplay between our planet's cosmic journey and the presence of interstellar dust could go some way toward explaining the occurrence of ice ages during these specific time periods, a vast, slow dimming and brightening of our star. Whatever the precise case, there is at least one other cycle, another profound and persistent rhythm that profoundly influences the arrival of ice ages on Earth. And this might perhaps be the most important for us today, offering a direct, tangible insight into the delicate balance of our planet's climate. It is the subtle yet powerful influence of the tilt of Earth's rotation, also known as obliquity. I already mentioned that this axis of tilt rotates around the planet, slowly tracing a circle in the sky over 26,000 years, a phenomenon we called axial precession. But it also subtly changes the angle at which it does this. Over the course of a vast 41,000-year cycle, the Earth's axial tilt alternates patiently shifting between a maximum angle of 24.5 degrees and a minimum of 21.1 degrees. Imagine our planet as a spinning top, sometimes leaning a little more deeply, sometimes sitting a little more upright. At the moment, our Earth's tilt is approximately 23.4 degrees, and it is gradually imperceptibly declining. You might think quite reasonably that this lessening tilt, this subtle straightening of our planet's cosmic posture, is a good thing. Surely the smaller the angle of tilt, the less extreme our seasonal temperature variations might be. Our winters would become milder, our summers cooler, leading to a more temperate, stable climate. Surely that would be a beneficial thing for avoiding the onset of monumental ice ages, a path towards perpetual warmth and comfort. Surprisingly, and this is where the profound subtlety of Earth's climate system truly reveals itself, it is quite the opposite. Left to its own devices, this lessening tilt, this gradual straightening of our planetary posture, would, in fact, gently lead us into another grand spreading of the ice sheets and a widespread cooling of the planet. This cooling trend would hit its peak in approximately 9,800 years, a distant whisper in our future, but a profound shift nonetheless. The counterintuitive truth lies not in the harshness of the winter, but strangely enough in the mildness of the summers. You see, when winters occur, particularly in the high latitudes and polar regions, snow builds up at the top of mountains and across vast expanses of land. This snow, crisp and white, settles and accumulates. In normal warm summers, this snow tends to melt away, retreating, allowing the underlying land or water to absorb the sun's warmth. However, if the summer is mild enough, if the sun's rays are just a little too weak, or its warmth not quite persistent enough, then the accumulated snow sticks around. It doesn't fully melt. This residual snow then becomes a more permanent feature of the landscape, growing year after year, slowly forming vast ancient glaciers and ice sheets. And here's where a powerful feedback loop, a true snowball effect, begins to unfold. Icy snow is inherently white in color and highly reflective, a brilliant mirror to the sun's incoming energy. This means that light, instead of being absorbed by the darker land or ocean beneath, has a strong tendency to bounce off it, reflecting much of the sun's warmth directly back into space. As more snow and ice accumulate, covering more of the Earth's surface, more sunlight is reflected. This actively makes the planet even colder, further reducing summer melt, thus creating conditions for even more ice to form. It's a self-reinforcing cycle, a powerful feedback loop that can accelerate a cooling trend, pushing the planet deeper into an icy embrace. We are right now in what scientists call an interglacial period. This is a brief, precious moment of warmth, a respite from the deeper, more pervasive cold trend that has characterized much of Earth's recent geological past. This period of warmth typically lasts a few tens of thousands of years or so, a fleeting golden age sandwiched between vast epochs of ice. In a technical sense, if it wasn't for this warmer uptick, we would actually be in an ice age right now. And from a truly precise, technical perspective, our planet actually is in an ice age, just one we're not fully noticing, because we happen to be living in one of its temporarily warm phases. For much of human history, indeed, across the history of mankind's entire existence, our species would have experienced ice covering vast tracts of the northern hemisphere, were it not for this briefly warm interglacial period. But this period of warmth, thanks to the very same Milankovitch cycles that brought it, will someday end. The subtle tilt will continue its decline, the orbit will subtly shift, and the cumulative effects will gently, inexorably push our planet back towards a deeper cold. Then winter will truly come for Earth, a winter spanning millennia, reshaping landscapes, and challenging life in profound ways, a return to the planet's long-term default state of glacial periods. Of course, this profound prediction rests on the assumption that Milankovitch cycles are the only factors that significantly influence global temperatures. And while broad trends lasting 100,000 years and interspersing warm upticks every 41,000 years are indeed demonstrable and remarkably consistent in parts of the fossil record, a testament to their powerful long-term influence, the location and orientation of our planet are not the only things that matter. Another profound driving force behind global temperature fluctuations operating on different timescales are the levels of certain gases in our atmosphere, carbon dioxide, CO2, and methane CH4. These are what we call greenhouse gases, and they act like an invisible blanket, gently trapping heat within Earth's atmosphere. If we're not careful, just as an ice age can build up with a powerful snowball effect, stripping away of ice can happen in the same way, but in reverse, accelerating a warming trend. Less ice means less reflection of sunlight, allowing the darker land and ocean to absorb more heat, making things overall warmer. This warmth then leads to even less ice, creating another powerful feedback loop, a warming spiral. It's a delicate balance where the amount of reflective ice plays a crucial role in regulating Earth's temperature. If Milankovitch cycles were the only factor in action, our future would indeed be cold. The Milankovitch cycles affecting the planet currently are mostly working to stabilize the system, leaving us in a temperate, relatively even temperature zone, a gentle reprieve from deeper cold. However, there will come a time in the distant future when their combined influence will shift and they will make temperatures hotter and colder, pushing the planet towards more extreme conditions. We would do well to keep these vast patient cycles in mind, for they are the grand conductors of Earth's deepest climate rhythms operating on timescales beyond our immediate comprehension. Milankovitch cycles are in it for the long haul, shaping the planet's destiny over eons. Winter might not be coming for a long time in the sense of a grand ice age, but one day our planet will face such a winter again. It is an immutable truth, written in the silent, swirling dance of the cosmos. It's getting hot outside nowadays, isn't it? It feels as though the very air is holding its breath, warmed by an unseen hand. It's difficult to turn on the news without hearing someone talking about global warming. Headlines are filled with references to rising temperature levels, the profound impact of fossil fuels, and an encroaching sense of danger that whispers in the background of our collective consciousness. The discussion around this subject has understandably grown as heated as the very weather it describes. This has been a topic I've been wary about weighing in on, simply because of how sensitive a subject it has become in recent times, fraught with strong emotions and deeply held beliefs. I've sat on this particular video like a quiet thought simmering in the back of my mind for 3 years, occasionally updating it with new insights, but never quite feeling it was the right time to release its gentle message. I didn't want to simply create more noise in an already clamorous world. However, I do now think there is something truly worth adding to this vital discussion, a different perspective that can enrich our understanding. After all, there is plenty we hear about the current temperature of the planet, the day-to-day fluctuations, the seasonal averages. But what is often not talked about, what frequently goes unexamined, are the ancient patterns of temperature change that existed in the profound depths of the past. These ancient rhythms provide a crucial context for that modern temperature, allowing us to see our current moment, not in isolation, but as a single frame in a vast unfolding cinematic history. Are we truly the hottest we have ever been? It's a compelling question, one that invites us to look beyond our immediate experience and into the deep memory of the Earth. Scientists believe that in the last 100 years, the global temperature has indeed been increasing, a rapid discernible uptick. But how does this relatively recent warming fit into wider, grander patterns and trends that span millions of years? And how, you might wonder, did they even find any of this out? How can we know what the temperature was 1,000 years ago, or even 1,000,000 years ago, long before humans walked the scene with their thermometers and data logs? Join me, Alex Milan, as we take a closer look at the remarkable data that records the temperature history of our own planet. It's only by understanding the ancient past, by gently listening to the whispers of geological time, that we can truly contextualize the current discussion on global warming and begin to answer what exactly scientists are so worried about. This journey is not about judgment or blame, but about understanding, about connecting with the Earth's deep past to illuminate its present and future. So to begin, let us pose a deceptively simple question. How do we know what the temperature used to be? It's easy enough to find the current global temperature today. All you need is a thermometer, a small everyday instrument, and you can step outside and take a reading. With enough readings taken patiently at different locations around the globe, from bustling cities to remote tundras, scientists can compile and find an average temperature for the whole planet. This methodical approach has allowed scientists to maintain fairly accurate records on average global temperatures since around 1850, a relatively recent blink in geological time. However, mercury thermometers, those ingenious devices that allow us to measure the air's warmth, were only invented in 1714. So how do we possibly know what the temperature was before these widespread global readings started being taken? How do we fathom the temperature 1,000 years ago, or even 1,000,000 years ago, long before humans were even a prominent feature on the Earth's stage before our bustling civilizations and our curious instruments? The answer, or at least a partial answer, is remarkably elegant and speaks to the Earth's own meticulous record-keeping. Scientists can approximate global temperatures in the distant past through a fascinating technique called ice coring. Imagine, if you will, vast ancient glaciers in places like Antarctica or Greenland, colossal sheets of ice that have been accumulating for hundreds of thousands, even millions of years. Essentially, when snow falls in these frigid, unchanging regions, because it is light and powdery, it traps tiny, pristine bubbles of air where it lands. If this snow doesn't melt, but has more snowfall on it later, year after year, century after century, you end up with incredible stratified layers of compacted snow and ice, each layer preserving a snapshot of the atmosphere from the time it fell. It creates something akin to the rings on a venerable old tree, each ring telling a story of a year gone by. By carefully collecting these cylinders of ice, known as ice cores, scientists can extract sections like taking slices from a giant frozen cake. These sections are then brought to a laboratory where they are gently, meticulously melted. As the ice melts, it releases the tiny ancient air bubbles trapped within air. that relates to specific years, sometimes hundreds of thousands of years ago. They then can measure the different ratios of gases released from these ancient air bubbles, which tells them the atmospheric composition at that precise moment in Earth's history. For example, they can measure the levels of carbon dioxide, methane, and oxygen. And here's the clever part, because we can test how much heat is retained by a gas when exposed to a constant temperature like the sun's warmth. For instance, we know that CO2 retains more heat acting like a warm blanket, while oxygen retains less. With enough of these precious samples taken from various depths, scientists can calculate roughly what the global temperature was during that specific year, tracing a precise icy line through Earth's deep past. The deeper the core, the further back in time we can see, accessing the frozen memories of our planet. However, the oldest glaciers, those magnificent frozen libraries, are only 1 million or so years old. To truly grasp the grand trends that govern global temperatures, we're going to have to journey back much, much earlier than that into the realm of truly ancient whispers. So how do we know what the global temperature was over 1 million years ago, long before even the oldest ice had formed its pristine layers? The answer might surprise you, and it involves a tiny, humble creature of the sea clams. Well, actually, not clams, but something remarkably similar. It's a tiny single-celled organism, no larger than a full stop on this page, called foraminifera, often affectionately shortened to forams. Like clams, these remarkable organisms produce delicate, intricate shells around themselves. And here's the crucial detail. These shells are slightly porous, acting as miniature natural archives. Oxygen, in particular, is taken into the shell and subtly trapped there, its isotopic composition reflecting the temperature of the water at the time the shell was formed. Crucially, this oxygen remains in place undisturbed, even when the foraminifera dies and its tiny shell settles onto the ocean floor, becoming part of the vast sedimentary layers. So using a similar process to the ice cores, if scientists can find shells of dead foraminifera from a particular year, or rather from a particular layer of sediment, corresponding to a specific time period, they can analyze the oxygen trapped within. This process is slightly different. Instead of air composition, scientists are looking at different oxygen isotopes, subtle variations in the atomic structure of oxygen molecules that are sensitive to temperature. But basically, it's a very similar process of decoding ancient environmental conditions from preserved natural archives. Foraminifera are still around today, thriving in our oceans, and they first came onto the scene a staggering 500 million years ago. This incredible longevity makes them instrumental, truly invaluable, in helping us get a clear, detailed picture of global temperatures during this much longer time period. Stretching back into the deep, deep past, they are the tiny silent scribes of the ocean, diligently recording the temperature of their watery world for 500 million years. But what is that picture? What does this ancient diary of the Earth reveal about its temperature history? Based on data meticulously collected and analyzed from countless foraminifera shells, it looks something like this: a vast undulating graph, a grand sweeping melody of warmth and cold across the eons. There is, of course, a certain degree of uncertainty to these findings. The data gets more reliable, more granular, the closer we get to the present day, as the archives are fresher and more accessible. But as you can clearly see from the general trends, the Earth's temperature has undergone significant dramatic changes over the last 500 million years. At times, the Earth's average surface temperature has soared to a scorching 14 degrees Celsius, hotter than we have today, a world vastly different from our own. And at other times, it has plummeted to about 5 degrees Celsius lower than today, turning much of the planet into a frozen realm. So no, we are clearly not the hottest we have ever been. Then again, that's not surprising to anyone who knew that the surface of the Earth when it was just formed was mostly molten magma, a fiery, inhospitable landscape. But you may not have expected these profound fluctuations. These immense swings between warmth and cold occurring so far back in time. Why are they happening? Scientists are not entirely sure, and this is where the profound mystery of Earth's deep history truly invites our wonder. There doesn't seem to be a single simple pattern to them on this grand multi-million-year scale, but they believe that some of these ancient fluctuations are profoundly linked to the emergence of new life forms, the subtle yet powerful influence of biology on geology. For instance, the momentous arrival of plant life on land at around 450 million years before the present might explain why the global temperature dropped so significantly then. These pioneering plants began absorbing vast amounts of atmospheric CO2, that potent greenhouse gas, and in turn released oxygen, a gas that retains less heat. It was a profound act of planetary engineering by life itself, subtly reshaping the atmosphere and the climate. Other profound changes in Earth's temperature could have been caused by the slow, inexorable movements of plate tectonics and intense volcanic activity events that reshape continents and pump enormous quantities of CO2 into the air, acting like a vast natural thermostat. And still other dramatic changes could have been caused by catastrophic cosmic events, such as possible meteor impacts, like the colossal one that wiped out the dinosaurs 66 million years ago. Each of these profound events left its indelible mark, a deep scar in Earth's temperature record. However, this is not the full picture. By increasing the resolution by zooming in slightly on this grand tapestry of time, we begin to see another interesting, intricate trend emerge. Let's look at the 65 million year picture stretching back to the time of the dinosaur extinction. Within the large sweeping changes, it turns out that there are many smaller fluctuations, a more rapid oscillation between warmth and cold. These become even more obvious, more pronounced, when we zoom in again and again and again, refining our view of the data. By this point, we can discern a distinct smaller pattern occurring. Rapid rises in global temperatures, followed by gradual dips. It's hard to truly get your head around the sheer scope of the Earth's history, the immense stretches of time involved. But each one of these dips, these profound downward movements on our temperature graph, represents entire ice ages. Ice ages are technically defined as any point in Earth's history where there is ice on the polar caps, something that is not always the case, as surprising as that may sound for our familiar blue marble. So technically, as I've mentioned in a previous video, we are in an ice age right now, simply because ice persists at both poles. However, although the general trend of the Earth's temperature at the moment over these vast timescales is indeed towards ages of ice, we are in something known as an interglacial period, a span of many thousands of years, where the Earth is temporarily warmer, a brief reprieve in between full ice ages. In the last full ice age, the colossal polar caps reached far south, enveloping vast stretches of the UK and parts of the US in thick sheets of ice, reshaping their landscapes and their very destinies. But what is causing these distinct dips and rises on our graph? These more regular oscillations that punctuate the deeper past? Well, I go into more detail about this in my video on Milankovitch cycles, which you can explore further. But just to brush up on them very quickly here, Milankovitch cycles are the periodic changes that take place within our planet's climate due to subtle fluctuations in its orbital movement around the Sun, usually over the course of thousands of years. These are the subtle wobbles, tilts, and stretches of Earth's cosmic dance that we began to explore in the previous chapter. Surface ice profoundly affects the temperature of a planet. The more surface ice a planet has, particularly in its high latitudes, the colder the planet tends to be. This is because ice is highly reflective, like a giant white mirror. It reflects more heat back into space, rather than absorbing it, a powerful feedback mechanism. But equally important is the direction that surface ice is facing. Consider ice to be like a shield that will reflect the sun's rays. If that ice is not pointed in the direction of the sunlight, or if the sunlight strikes it too obliquely, it can't reflect it effectively. So anytime the planet points its surface ice more directly towards the sun, the Earth tends to get cooler. creating something of a feedback loop, the albedo effect at play. This matters because the Earth's axis isn't stable. Over the span of thousands of years, it moves back and forth, sometimes pointing the polar ice caps more towards the sun, and sometimes subtly pulling them further away. Although this change is only a couple of degrees at most, a mere whisper of a shift in its angle, it is enough that over time it has a profound impact on the global temperature. The temperature drops as the ice shield faces the sun more directly, reflecting more heat, and rises again as it points away, allowing more heat absorption. This fluctuation is one clear example of a Milankovitch cycle in action, driving the waxing and waning of glaciers. There are other Milankovitch cycles too, which are consistent rhythms in the Earth's orbit that affect its temperature, acting on grand timescales of 23,000, 41,000, 100,000, 45,000, and even 2.4 million years. Whenever these various cycles, these different planetary rhythms coincide with each other, they create even greater changes to the global temperature, amplifying the swings between warmth and cold. You can see, for instance, that the gaps between the ice ages in this graph tend to be about 100,000 years apart, perfectly in line with one of the dominant Milankovitch cycles, specifically the change in the Earth's orbital eccentricity, the subtle stretching and contracting of its path around the sun. But all of these intricate cycles have a subtle yet profound impact on the Earth's long-term temperature story. So where are we in relation to one of these Milankovitch cycles? Right now, let's zoom in some more, focusing our gaze on the most recent chapters of Earth's temperature diary. As you can see, we have risen out of an ice age, emerging from its cold embrace, and have entered a fairly stable plateau of global temperature. This is entirely consistent with the rapid rise in temperature followed by a slow drop in temperature that characterizes ice ages, and the periods between them, a familiar pattern etched into the Earth's memory. All of recorded human history, from the construction of the ancient pyramids to the present bustling day, can be found on this relatively stable warm plateau. Although humans existed before this point, they hadn't really got the hang of building any grand civilizations. Or perhaps the conditions weren't as conducive to their sustained flourishing. Scientists have named this warm plateau, this cradle of human civilization, the Holocene period. However, the uptick right at the very end of this plateau, a sharp, almost vertical climb on our temperature graph, is not so usual. This recent uptick represents a rise in the global temperature by approximately 1 degree Celsius, which technically is still roughly on par with the peak of the interglacial period before our current one over 100,000 years ago. So in terms of absolute temperature, it's not unprecedented in Earth's deep past. However, it is not the temperature change itself that is concerning about this recent uptick. It is how quickly it is rising. Unlike all the other changes on all these graphs, which have taken place over hundreds of millions of years at the longest and thousands of years at the shortest, this particular rise took place in a mere 100 years, a blink of an eye in geological time. This incredibly rapid change, this sudden surge, could have a profound disruptive impact on the intricate ecosystems on the planet, straining life's ability to adapt. So what could have caused this astonishingly rapid uptick? The answer cannot be Milankovitch cycles, for as you have seen, these cycles take place on the scale of thousands of years at least, and millions at most. They are the great slow forces of the universe. Even when we zoom in on sections of our graph where there appear to be sharp upticks, we realize that these rises take place over a couple of thousand-year periods, gradual by human standards. Milankovitch cycles are aptly described as weak but consistent forces, like the slow patient trickle of a stream that eventually over eons erodes a colossal mountain. They do not by their very nature create profound effects over such a minuscule time frame as 100 years. Similarly, there has been no recent cataclysmic event, such as the one that famously wiped out the dinosaurs. That ancient meteor was thought to be a staggering 10 kilometers wide and struck with the unimaginable force of 21 to 921 billion Hiroshima A-bombs, a truly planetary wound. About 75% of species tragically died in the profound climate change that happened in its aftermath, a global catastrophe. If something like that had hit Earth since 1850, we would most certainly have noticed it, for its effects would have been undeniable and immediate. However, there is one profound factor that does perfectly explain this sudden rapid change in global temperatures: the activity of humans. It is not the first time that living organisms have had a profound impact on the global temperature. Remember, it is believed that some of the vast changes we see in Earth's ancient temperature record were caused by the introduction of plant life absorbing CO2 and releasing oxygen. Similarly, back when life was still all single-celled organisms about 2.4 billion years ago, the momentous arrival for the first time of cyanobacteria that could photosynthesize had a massive transformative impact on the atmosphere. For the first time, an organism started putting vast quantities of oxygen into the atmosphere, changing its fundamental composition. This occurred at such a rapid rate that there was an event known as the Great Oxidation Event, which profoundly coincided with a significant drop in the global temperature. Some scientists even believe the entire world almost froze entirely over becoming a snowball Earth, as it came to be known, as there is evidence of glacial activity even at the equator. What we learn from this profound history is that the balance of global temperatures is incredibly delicate, a subtle equilibrium easily swayed. A single species, if it begins to change the atmospheric ratio of gases on a vast enough scale, can have a massive impact, profoundly overloading the subtler, slower effects of Milankovitch cycles. And since 1850, since the dawn of the Industrial Revolution, humans have definitely changed the way we have been interacting with the atmosphere in profound and unprecedented ways. Unlike the previous roughly 10,000 years of relatively stable human history since 1760 and the Industrial Revolution, human activity has produced vast amounts of greenhouse gases as a waste product of industrialization, transportation, and farming. These gases, carbon dioxide and methane primarily, have been pouring into the atmosphere at an accelerating rate, changing its very composition. In the last 4 decades, each decade has remarkably been the hottest decade on record since we started tracking global temperatures in 1850. CO2 levels are now at a global average of 410 parts per million, and methane at 1 to 866 parts per billion. This is higher than we have seen in the last 800,000 years, which means since before about 8 ice ages and the interglacial periods between them. It is a profoundly unusual concentration, a testament to the rapid changes we have introduced. And importantly, the global cover of surface ice, those powerful reflectors of sunlight, has been retreating consistently since 1950, something scientists do not believe to have happened for the last 2,000 years. As you will recall, this has a knock-on effect on Milankovitch cycles. For a planet with less surface ice does not reflect as much heat from the sun, so it tends to get even hotter, accelerating the warming. It's like pushing a cart down a hill. These changes have a certain amount of momentum to them, building upon themselves. Sadly, rapid changes in global temperature, regardless of their cause, tend to lead to species going extinct. It normally takes thousands of years for life to adapt to profound changes in conditions, from a massive, woolly mammoth adapting to the cold of an ice age to a desert-dwelling elephant adapting to today's warmth. Natural selection, that patient sculptor of life, takes time, often millennia, to develop in a species the traits they need to thrive in a new environment. If species are not given this crucial time, if the changes happen too quickly, they either have to migrate rapidly to a new environment better suited to them, or they will tragically die out. As the habitable zones begin to migrate towards the poles, some zones will vanish completely, and new hot desert environments will be created that life in general is poorly adapted to. It's a race against time for countless forms of life. It's important to note that these events are not unstoppable. Global temperature change does have some momentum, a certain inertia, But if we as humans find ways to stop changing the atmosphere's ratio of gases, then in time, the powerful slow forces of Milankovitch cycles will take over again, and the rapid rise will stop. That's why it's so important for governments, for communities, for individuals to listen to reports by institutions like the IPCC, the Intergovernmental Panel on Climate Change. This is an international group of thousands of scientists, funded by multiple governments, tasked with finding out the realities of climate change, distilling complex data into clear assessments. In 2021, they released their 6th assessment report, explaining the physical science basis of climate change. In it, they unequivocally stated that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. The evidence, they concluded, is undeniable. However, they also offer suggestions, not despair. Namely, they emphasize the critical importance of halting or rapidly reducing CO2 emissions towards net zero, for CO2 is the largest contributor towards climate change, followed closely by methane. They also recommended the widespread development of carbon dioxide removal facilities to be established worldwide, technological solutions to complement emission reductions. Some of these are already in operation, such as Project Longship in Norway, a pioneering effort. Their aim is to take CO2 out of the atmosphere and bury it safely beneath the ground into depleted fossil fuel reservoirs, literally putting the carbon back where it came from. The IPCC says that actions like this, if widespread enough, will reduce global surface temperature and even begin to reverse certain other destructive processes. Like the acidification of the oceans, a silent threat to marine life? Personally, I'm not super convinced by current carbon capture projects as a sole solution. They face immense scale challenges, but they do exist and represent one facet of a multi-pronged approach. Ultimately, my aim for this video was to examine what global warming meant within the context of Earth's wider history, to place our current moment within the grand tapestry of planetary time. From it, we can see that it's not actually accurate to say that we're the hottest we've ever been. And I find that a really fascinating insight, a piece of perspective that can sometimes be lost in the daily headlines. However, that fact alone is not the reason some people think it is to not worry about the problem. Climate change, as we've seen, is a process that usually takes millennia to unfold a slow geological tempo. I've realized the worrying part is not necessarily the change itself, for change is a constant in Earth's history, but rather the speed at which it is happening. Some life forms, simply put, might not be able to adapt quickly enough and will get left behind. And how will humanity cope? We don't fully know, as we haven't been around long enough to deal with the extremes of the past in a global, interconnected civilization. While human activity has undeniably sped up certain elements of this temperature change, and while we can undo some of what has been done through our actions, now some things like higher sea levels due to melting ice will be with us for up to 1,000 years, according to the latest IPCC report. We are, according to the science, past the point of no return for limiting warming to 1.5 degrees Celsius above pre-industrial levels, and will need to make rapid fundamental changes to our society this decade to stop it going any further than that. This will be hard and immense global undertaking. There's no way we, as a species, will be able to achieve this hard path unless we can agree on the facts that underpin it, though. Without the broader context of agreed-upon data, it will forever be perfectly possible to arrive at a wide range of conclusions and different paths we should take, leading to inaction and division. That is why, when it comes to any discussion, context is so important. By looking at the vast undulating pattern of our planet's history, we see that the current uptick in global temperatures is an induced event, a sudden sharp deviation that doesn't match already existing natural patterns. And it perfectly coincides with the profound global scale of human activity. Debate what you want to do with that information and the best path to take in light of it. But these are the facts set in ice and the silent bones of organisms long dead. They will brook no argument. They simply tell a story etched in the very fabric of our Earth, inviting us to listen and respond. When I started my Milankovitch cycle contemplation with a reference to Game of Thrones, I didn't realize exactly how apt my analogy was. In that television show, the armies of the Night King in the north are trapped behind a giant wall, a colossal barrier of ice and magic. And just like in the TV show, it turns out that on Earth, there exists a powerful icy force to the north that is constantly seeking to overthrow its bounds and rush southward. That powerful winter is also kept at bay by a mighty unseen wall, one that allows the nations to the south to enjoy relatively tranquil, temperate conditions. And just like in the TV show, that wall, on occasion, eventually gets breached, leading to a wave of ice and biting cold that sweeps down and threatens the lives of all those in its way. You might not immediately recognize what I'm talking about. Where is this wall, and what is the icy winter it protects us from? The answer to the first question is a name that I find particularly cool, imbued with a sense of cosmic power, the polar night jet. And it turns out that the icy force it protects us from the polar vortex is a biting chill not to be underestimated. What exactly is this polar vortex, and how does the polar night jet protect us from its icy embrace? Join me now as we learn more about this climate-shattering phenomenon and what happens whenever the polar night jet breaks down, unleashing the polar vortex upon unsuspecting lands. There are actually two polar vortices, immense swirling masses of cold air, one at each pole of the planet. And even there, each vortex comes in two distinct parts, like layers of a magnificent invisible onion. First, there is the tropospheric polar vortex, a powerful cyclonic swirl of air spinning in the section of the atmosphere closest to the ground, known as the troposphere. This layer extends from ground level up to about 10 to 15 kilometers, or roughly 6 to 9 miles high. This is where 75% of the total mass of the atmosphere resides, where all our familiar weather happens, where clouds form, and where planes fly. Above that, quietly residing in its own realm, lies the stratospheric polar vortex. This is a technically separate weather phenomenon with its own immense size, seasonal cycle, and profound influence on the global climate, interacting subtly with its lower counterpart. Each of these massive cyclones sits serenely over its respective pole, spinning in majestic synchronicity with the planet's rotation. Within their vast swirling currents, wind speeds can reach astonishing velocities, up to 240 kilometers per hour, or about 150 miles per hour. Imagine a truly colossal invisible top spinning ceaselessly at the very ends of our world. But why do these powerful winds happen? What orchestrates this magnificent swirling dance of cold air? The first crucial piece of the puzzle lies in temperature difference. Imagine our planet as a grand canvas painted with varying degrees of warmth. At locations like the equator, where sunlight is most concentrated, striking the Earth's surface most directly, the air is warmed intensely. As it warms, it becomes lighter, less dense, and naturally starts to rise like a gentle, unseen breath escaping from a vast heated surface. As it does so, it creates an area of low pressure beneath it, a subtle invitation that gently draws air into it from its surroundings, much like a giant, silent vacuum cleaner, steadily humming across the land. Meanwhile, at places like the poles, where the sun's warmth is diffused and gentle, striking the surface at an oblique, glancing angle, the air is much colder. This frigid air is denser, heavier, and naturally contracts, gently falling back towards the surface of the Earth. This creates zones of high pressure where air molecules, feeling the gentle press of their neighbors, wish to spread out to expand into available space, like a crowd of sleepy school children finally released into a wide open field after a long day. So naturally, with these two fundamental forces constantly at play, the powerful rising warmth at the equator and the subtle, persistent falling coolness at the poles, there is an inherent tendency for air to rush from the high-pressure poles towards the warmer low-pressure region of the equator. Imagine freezing cold winds, born of the deepest chill, constantly trying to escape from the north and south poles, yearning to find warmer, more expansive homes. However, as we discussed in our previous contemplation, This model is a little simplified, a mere sketch of a much grander masterpiece. For wind does not simply travel in one continuous straight line from the pole to the equator. Instead, because air rising from the equator begins to cool and descend much sooner than expected, around a latitude of 30 degrees both north and south, and similarly, air from the poles warms and rises earlier at around 60 degrees latitude. The atmosphere resolves itself into 3 distinct cells of air circulation in each hemisphere. These are the graceful Hadley cells, where air masses above the equator rise, move poleward, cool, and descend. Then there are the polar cells, where cold air at the poles descends, moves equatorward, warms, and rises. And nestled between these two, like a quiet intermediary, is the Ferrel cell. Unlike its temperature-driven companions, the Ferrel cell is not directly powered by heat differences. Instead, it is gently dragged along by the rotation of the Hadley and polar cells, much like a quiet gear in a vast unseen clockwork, and it rotates in the opposite direction to their motion. In terms of our northern polar vortex, which we are focusing on, this means that once the cold air from the pole begins its journey southward, it eventually encounters warmer wind traveling in the opposite direction. And when two vast air fronts, born of different temperatures, meet, they don't simply mix and blend. Oh no, they clash like two grand opposing armies meeting on an invisible battlefield, creating powerful boundaries and defining distinct zones. So the polar vortex, even in its normal state, finds itself gently contained, bounded, clashing softly against winds, coming in from all sides, a dynamic equilibrium of opposing forces. But there's more at play here, a second profound force that truly redirects those winds, spinning them into the powerful vortex that keeps them circling the poles, rather than rushing directly down towards the equator. Where does this majestic spin come from? It's due to something known as the Coriolis force, that subtle yet powerful consequence of Earth's rotation. In a simple imagined flat world, cold wind from the poles would indeed travel directly towards the equator, while warm wind from the equator would simply float over it towards the poles. But the world isn't a simple flat sheet. It's a majestic rotating sphere. You're traveling right now wherever you are at a certain speed due to the Earth's rotation. If you're at the very pole, you'd have 0 kilometers per hour of eastward speed, merely rotating on the spot. But if you're at the equator, you're moving eastward at a breathtaking 1,600 kilometers per hour. You might not notice this fact because everything next to you is on average traveling at the same speed in the same direction, like passengers on a smoothly gliding ship. But imagine what happens if you or a vast parcel of air were to travel from the equator towards the pole. The principle of conservation of momentum gently whispers that you would still be traveling eastward at roughly the same speed as previously carrying that initial momentum. But suddenly, as you move poleward, the Earth beneath you is not traveling quite so fast in an eastward direction. Remember, at the pole, you'd have 0 eastward speed, simply rotating slowly. So, if on the other hand, you keep all your eastward momentum from the equator and travel towards the pole, suddenly it will appear, compared to everything else, moving at a slower eastward pace, like you are traveling east really fast. In practice, this profound principle means that air that travels up towards a pole from the equator, whether towards the North Pole or the South, will not go straight up. Instead, over large distances, it will start to curve gracefully towards the east. This rapidly eastward traveling air is why you get jet streams. These are not just currents of air. They are powerful invisible ribbons, vast rivers of wind, carving precise paths across the skies. There are at least 4 of these magnificent high-altitude rivers of air, gracefully straddling the gaps between the Hadley cells, the Ferrel cells, and the polar cells. The subtropical jet stream lies between the first 2, a little weaker, a gentle whisper of the wind's power. But the jet streams we are primarily interested in are the polar jet streams, those formidable rings of fast-moving air embracing the frigid air that develops in the North and South poles. These majestic ribbons of air encircle the globe in an almost continuous undulating path a little underneath the boundary between the troposphere and the stratosphere, that quiet layer above our everyday weather. They are surprisingly thin, only a few kilometers deep, like a delicate thread drawn across the vast canvas of the sky. Yet they can be hundreds of kilometers wide, a vast unseen highway of wind. And in their very hearts, the wind can surge to astonishing speeds, reaching up to 400 kilometers per hour. As a gentle reminder, speeds over 120 kilometers per hour are already considered to be the strength level of hurricanes. These are truly colossal forces, shaping the very air around our planet with unseen power. The jet stream around the South Pole is remarkably stable, more consistent in its embrace. Its powerful winds overrule the polar winds, trying to leave the polar air mass whipping them along with it and dragging the entire polar cell into a massive Antarctica-spanning vortex. It is a testament to the South's unique geography, with a large cold landmass surrounded by ocean, creating a more consistent, contained swirling of air. This stability means that the southern polar vortex rarely strays from its icy domain. At this point, a keen-eyed observer might have noticed a subtle yet intriguing flaw in this model. If the conservation of momentum means that air going from the equator towards the pole gracefully veers towards the east, why is it that air traveling from the pole towards the equator doesn't do the exact opposite? After all, it has virtually zero momentum moving to zones that have considerably more momentum comparatively. It should logically be quickly left behind, appearing to start spinning to the west. This is a perceptive question, and indeed, it is true. However, cold winds as they begin their journey from the pole encounter much more friction. As this dense, heavy air starts to slide underneath the warmer front, seeking its path towards the equator, it also drags along the ground, interacting with the Earth's surface. This constant friction seems to slow it down enough that the powerful countervailing jet stream, circling high above, gently overrules it, maintaining the overall eastward flow. It's important to note this subtle tension at play, though, for it becomes much more important in the phenomenon we call the polar night jet. The polar night jet is the specific jet stream that elegantly bounds the vortex at the North Pole. Specifically, it bounds the stratospheric polar vortex, the upper layer of the swirling cold air. It is the invisible wall, the magnificent guardian that keeps the most frigid air masses safely contained during the coldest part of the year for the North. During the winter months in the North, the sun, our great source of warmth, is absent from the sky entirely for extended periods. This prolonged lack of sunlight creates even more intensely freezing temperatures, a profound chilling of the air. Interestingly, this colder climate creates a deeper pressure difference between the air around the pole and the air further south, and this enhanced pressure gradient actually strengthens the very forces that create the polar night jet, making it an even more formidable wall, a more robust containment system. Meaning that, during the coldest part of the year, this vast freezing air is usually remarkably well contained, a testament to the strength of its atmospheric prison. However, as with all things in the delicate dance of Earth's climate, this containment does not always hold true. There are forces subtle and grand that can disrupt a jet stream, causing its steady path to waver and buckle. Imagine a powerful river flowing smoothly, suddenly encountering obstacles. Certain zones on Earth, like the vast, dynamic boundary between sea and land, where two vastly different surfaces meet and exchange energy, can create their own localized winds, which can subtly tug at the jet stream like gentle eddies, pulling at a powerful current. Similarly, the imposing presence of a large mountain range, a colossal upheaval of the Earth's crust, acts as a physical barrier. It doesn't just block the wind, it forces an entire air current to elegantly move around it, creating ripples and diversions in its otherwise smooth flow. Even other powerful weather phenomena like El Niño, which we touched upon earlier and will explore more deeply later, can have a profound, subtle impact on the path the jet stream chooses to take. It is a reminder that everything is connected, and a change in one grand system can gently nudge another. The jet stream in its essence is not fixed rigidly in place. It is a dynamic balancing point, a continuous negotiation between a range of opposing forces. When it encounters such obstacles, or when the subtle atmospheric pressures shift, it causes it to subtly deviate from its course. And once it begins to deviate, it is like a vast invisible string that has begun to bounce. It shifts no longer perfectly in its delicate balance and overcorrects itself, then finds itself out of balance again, leading to another overcorrection. This creates immense, slow-moving planetary waves, like giant ripples spreading across the atmosphere. These are the graceful undulating movements that cause the polar night jet to gently meander around the Earth. Rather than traveling in a perfectly straight line, its usual elegant curve replaced by a more erratic path. And these elegant oscillations can at times reach a point where there is a moment when the invisible wall gives way. The first gentle sign of this profound shift often comes in the form of a phenomenon known as a sudden stratospheric warming, SSW. Most common in late winter, an SSW can even represent a time where temperatures rise in the polar region by as much as 50 degrees Celsius over the course of just a few days, a dramatic, almost unbelievable thermal inversion. Something within the intricate system of the jet stream can be so thrown by this dramatic event that it leads to the southward moving westerly winds overpowering the jet stream, partially or completely reversing its flow. The powerful eastward flow falters, then struggles, and sometimes incredibly begins to move in the opposite direction. No longer contained by its majestic guardian Arctic wind, that deep ancient chill suddenly moves south, spilling out from its usual icy domain. As it encounters warmer and warmer air, it pushes faster and faster south in an attempt to balance the profound temperature gradient. The entire jet stream buckles its elegant curve, transforming into a series of profound loops and dips. And suddenly, it pivots massively, reorienting itself traveling down the planet so that regions like Europe and America, usually safely on the warm temperate side of the polar night jet, suddenly find themselves squarely in the domain of the polar vortex. The forces of winter in their purest, most biting form have truly arrived. In fairness, not all of these events are devastating. With sufficient preparation, you can simply put on some warm clothes, bundle up against the cold, or try to avoid going outside for the month or so that the polar winds are overhead. As long as you're ready for the cold, as long as you respect its power, it's not the end of the world. It's merely a temporary challenging visitor. However, sometimes the outcome is far more serious, etching itself into the collective memory of a region. Consider the UK in 2009 to 2010. During what became known as the Big Freeze, parts of Scotland experienced temperatures as low as 22 degrees Celsius, the coldest in nearly 40 years. This brought widespread transport disruption, grinding travel to a halt, event closures, and power failures that left many in the dark and cold. Sadly, this intense cold, this sudden powerful breach of the polar night jet, in turn, led to the tragic death of 25 people, a somber reminder of nature's formidable power. In the U.S., the 2019 January-February North American cold wave saw a polar vortex move down across much of the country, bringing similar devastating outcomes. Some areas saw temperatures as low as 50 degrees Celsius. If you take into account the wind chill factor from the blustery freezing winds exposure, could cause frostbite in just 10 minutes. Snowstorms raged, blanketing regions in deep snow, and life itself seemed to slow to a crawl. Sadly, another 22 people died during this event, with hundreds more needing urgent frostbite treatment. The raging polar vortex, in its unrestrained southward push, was responsible for this profound disruption. In time, the imbalances in the global temperature restore themselves, the vast atmospheric forces gently realign, and the jet stream eventually returns to its previous position, pulling the polar vortex back into its familiar contained domain. However, it's worth noting that some level of jet stream breakdown occurs in the North approximately 6 times every decade, making these events a relatively regular, albeit often subtle feature of Northern Hemisphere winters. If you live in the Northern Hemisphere, you will likely see many more of these events over the course of your lifetime, although hopefully not all as powerful and impactful as these two profound examples. In the South, you are likely safer. There have only ever been 2 instances in recorded history of the solar polar jet stream breaking down in the same way as the northern one, a testament to its greater stability. It has happened, though, and the precise mechanisms behind its rare breakdowns are not fully understood, adding another layer of mystery to our climate systems. It's difficult to say, as global temperatures gradually rise, what influence this might have on the jet streams themselves. Some evidence indicates that they are traveling further poleward on average year on year, perhaps in response to a warming Earth, although this is apparently not unheard of in the planet's long history. There is some more evidence that the jet streams have actually strengthened since 2002. If so, we should be grateful. Although unpleasant, the biting cold of the polar vortex usually is only a passing weather phenomenon. We see it return north within a month or so, a temporary inconvenience. But if the jet stream were to permanently go, if that magnificent unseen wall were to truly collapse, the polar vortex would come down from the north to stay, and we would truly know what it is like to live in Arctic conditions, a profound, permanent winter for much of the globe. The more I've learned about this subject, the more I've discovered that the winds of our planet are this fascinating, intricate weave of interplaying forces and effects that tug and pull on each other constantly, seeking perfect balances and yet constantly shifting in rhythms and patterns. And yet, it does so practically invisibly. So much is going on that we simply do not see down here on the ground, just because air is well air, a transparent, often unnoticed medium. And yet, I've learned its profound importance. The polar night jet is not just wind with a cool name. It is a bastion of protection, a formidable wall against the frozen wind, silently safeguarding our temperate lives. It really makes you think of the incredible majesty of the world around us. How much is going on that protects us, that we simply do not see, an unseen ballet of cosmic and atmospheric forces constantly at play, maintaining the delicate habitability of our precious home. Imagine a force so powerful that it can change weather patterns around the world and even alter the fate of ancient civilizations. It sounds like something from a grand myth, yet it is a very real, intricate part of our planet's living system. Earth's short-term weather patterns and its long-term climate are influenced by a complex collection of factors. These range from our planet's precise place in the solar system and its steady rotation to the intricate atmospheric patterns that sweep across its surface and the familiar comforting seasonal changes we experience each year. To further complicate things, every few years, our planet experiences the profound interplay of El Niño and La Niña events, 2 opposite ends of a single powerful scale that are part of the El Niño Southern Oscillation, or ANSO for short. Evidence of the ENSO's profound influence stretches back tens of thousands of years, whispered in the ancient chemical signatures, preserved in paleoclimate indicators like coral fossils and layers of ocean sediment. It may have even played a subtle yet significant role in destabilizing some of the world's great ancient civilizations, their rise and fall perhaps intertwined with its shifting rhythms. This suggests that understanding ENSO is not just about future predictions, but about unraveling the deep interconnected history of humanity and its planetary home. Just recently, one of the 5 strongest El Niño events ever recorded has finally come to a gentle end as of June 2024. For months, it brought with it record-high ocean temperatures, creating unprecedented heat stress on vibrant coral reefs, leading to widespread bleaching events. It ushered in parching drought in parts of the Amazon rainforest, turning lush green landscapes brittle and dry. And for North America, it brought extreme rainfall unleashing powerful atmospheric rivers with dangerous consequences, including landslides and flooding. Now, with La Niña predicted to begin late in 2024 or early 2025, a shift in the grand rhythm is once again on the horizon. What changes can we expect globally and locally as our planet prepares for this new phase? Join me now as we take a closer look at our changing planet, delve deeper into the intricate dance of the ENSO, and contemplate what La Niña will do to Earth. Our previous contemplation about El Niño explored one powerful side of this global cycle, a cycle that typically takes between 2 to 7 years to swing from one extreme to the other. These El Niño and La Niña episodes usually last for about 9 to 12 months, like a long drawn-out breath. But on occasion, they can extend for several years, leaving a more prolonged imprint on the planet. In this extended contemplation, we will take a closer look at how this magnificent cycle works, what those neutral periods truly mean, and what might happen as we gently head into the opposite extreme of La Niña in the coming months. When our Earth experiences average or typical conditions, not swayed by the extremes of El Niño or La Niña, we call those periods ENSO neutral. During these times, the sea surface temperature and the trade winds are near their average predictable conditions. It is a period of relative calm, a baseline against which the more dramatic ENSO events are measured. But every few years, subtle fluctuations in wind patterns and ocean surface temperatures can begin to signal the quiet beginning of an El Niño or La Niña event, marking a profound departure from Earth's normal expected conditions. These events, powerful in their scope, alter worldwide atmospheric patterns and are known to wreak havoc by contributing to extreme weather and significant environmental harm across the globe. Let us imagine for a moment that we are on the International Space Station orbiting high above Earth. From this vantage point, we can clearly see our planet's magnificent spherical shape and observe how sunlight, our primary source of warmth, affects the Earth's surface unevenly. More light and heat reach the Earth at the equator, where sunlight strikes most directly like a powerful focused beam. In contrast, at the poles, sunlight reaches our planet at a low glancing angle, diffusing its warmth over a much larger area. In the same fundamental way that a hot air balloon rises or hot steam ascends over a pot of boiling water, the same phenomenon happens along the equator. The direct, intense sunlight warms up the air. This hot, moist, low-pressure air, becoming lighter, naturally rises up into the atmosphere, ascending towards the sky. As this warm air gets higher, it begins to cool off and condense into clouds, forming those familiar fluffy white blankets that often gather in tropical regions. This is precisely why we see an abundance of lush, vibrant tropical rainforests concentrated close to the equator. The constant cycle of rising warm, moist air and subsequent condensation provides the continuous rainfall necessary for such rich biodiversity. As this warm air continues to rise, it gently pushes the cooler air away from the equator, guiding it subtly outwards towards the north and south, where it will eventually sink back down to the surface, having cooled and become denser. Then that cool descending air will flow from regions of higher pressure along the surface of the Earth, seeking areas of lower pressure, moving gently back towards the warmer rising air near the equator. This completes a vast, majestic atmospheric loop, a profound circulation known as the Hadley cell rotation. It is a fundamental global engine driven by the sun's direct energy, creating predictable patterns of wind and rainfall across the globe. But how does this worldwide circulation of air, so elegantly driven by the sun's warmth, relate to the powerful El Niño and La Niña events? The surface winds created by these Hadley cells are not straightforward north-south currents. Instead, as we explored earlier, they are deflected towards the equator. Due to the Earth's rotation, a profound phenomenon we call the Coriolis effect. It is this very effect that creates the famous trade winds on either side of the equator. Those consistent eastward blowing currents of air that span vast oceanic expanses. And it is changes to these very trade winds that serve as the crucial indicators, the silent signals of when we will experience the profound shifts of El Niño and La Niña events. Historically, the trade winds have been so remarkably reliable, so consistent in their strength and direction, that sailors for centuries used them to navigate the globe, their sails filled by these constant breezes, hence their evocative name. These winds were not merely currents of air. They were routes, highways across the vast open ocean, guiding voyages of exploration and trade across continents. The chemical signatures of the Enso cycle stretch back tens of thousands of years, whispered in the silent ancient archives of paleoclimate indicators like the growth bands in coral fossils, each band a tiny record of past ocean temperatures and atmospheric conditions. And remarkably, we have written records of the Enso as far back as the 1500s, etched into the observations of early explorers and chroniclers. Indeed, El Niño events may have even aided Spain in their conquest of the Incan Empire in the 1500s. The disruption brought by unusual weather patterns, perhaps leading to crop failures or widespread disease, could have weakened the empire, making it more vulnerable to external forces. And in the late 1700s, a series of powerful El Niño events likely contributed to widespread crop failures and social unrest that tragically sparked the French Revolution, a profound example of how climate can subtly yet profoundly influence the course of human history. Despite this long ancient record of Enso activity and the massive impact it has on worldwide weather and environments, it wasn't until the 20th century that we finally started to understand the complex mechanisms behind it. The first defining breakthrough came in the 1920s, thanks to the meticulous work of the British scientist Sir Gilbert Thomas Walker. He set out with profound dedication to better understand the strength of the monsoons in India, a vital climatic rhythm for the lives of millions. In his persistent search for a way to predict monsoon strength, he ended up documenting the Southern Oscillation, that repeating shift in air pressure that happens across the equatorial Pacific Ocean, a vast seesaw of atmospheric weight. This oscillation was part of another large-scale air circulation that had not been documented before, and as we discussed, was later named the Walker Circulation in his honor. Remember how I said that Hadley cells circulate air north and south? Well, the Walker Circulation is just like Hadley cells, except instead of moving air north and south, the Walker Circulation moves air to the east and west over the equatorial Pacific. And crucially, instead of being directly driven by sunlight and temperature differences, the Walker Circulation is primarily guided by the easterly trade winds and subtle shifts in ocean temperature. It would be 60 more years before scientists were able to finally connect these changes in air pressure over the Pacific with the alternating pattern of warm and cool surface water in the Pacific. This was the final crucial piece of the puzzle, bringing together ocean and atmosphere into a single unified understanding. Combine these two interconnected phenomena. The ocean temperature shifts and the atmospheric pressure changes make up what we now profoundly know as the El Niño Southern Oscillation, ENSO. El Niño refers specifically to the changes in sea surface temperature, and the Southern Oscillation refers to the simultaneous changes in air pressure across the Pacific. Unlike Hadley cells that reliably move air north and south in a relatively consistent pattern, the equatorial Walker Circulation is not consistent. It is a more delicate balance, and it can experience colossal dramatic shifts as part of the Southern Oscillation. Every few years, the surface temperature and the trade winds over the Pacific experience fluctuations, a weakening or strengthening signaling an oncoming shift in the Walker Circulation. In turn, these profound shifts, which we refer to as El Niño or La Niña events, can upset the delicate balance of weather and ecosystems over the entire Earth, sending ripples across continents and oceans. So what exactly happens to the Earth during each of these distinct phases? During neutral ENSO periods, those quiet in-between times, the sea surface temperature and the trade winds are near average conditions, a state of gentle equilibrium. During these periods, trade winds blow steadily across the Pacific Ocean like faithful shepherds, guiding warm surface waters to travel west from South America towards Australia and Asia. As that warm surface water moves west, pushed by the relentless winds, it makes way for deep, cooler waters to rise up in its place. This profound ocean circulation brings nutrient-rich, cool water to the surface in a process called upwelling, where it feeds vast blooms of phytoplankton, those microscopic plant-like organisms that form the base of the marine food chain. These phytoplankton, in turn, support other parts of the ecosystem, like vast schools of fish and the countless creatures that feed upon them. In neutral periods, weather across the world occurs more or less as expected, following its familiar rhythms. This can include normal hurricane development in the Atlantic, adhering to its predictable seasonal patterns, and average monsoon rainfall across Southeast Asia, bringing the life-giving water necessary for agriculture and daily life. The water circulation in its neutral state drives colossal columns of warm, moist air to rise up above southern Asia, northern South America, and middle Africa. So it's no coincidence that these three vast regions are precisely where we see a concentration of vast, lush rainforests, vibrant tapestries of biodiversity supported by consistent rainfall. The influence of this equatorial airflow is truly vast, shaping not just weather, but the very distribution of life. Thus, it's easy to imagine how even subtle changes to this grand system could cause a ripple effect around the world, sending tremors through ecosystems and human societies alike. The first subtle signs of trouble, the quiet whispers of change, are when the trade winds begin to weaken, losing their steady westward push, and sea surface temperatures begin to rise in the central and eastern Pacific. This can indicate an oncoming El Niño event, like the one we experienced in 2023 and 2024. During El Niño, the colossal columns of warm air that normally rise above our world's rainforests are shifted dramatically to the east or west, disrupting their usual patterns. This profound change disrupts Asia's vital monsoon season, leading to prolonged droughts and severe water scarcity, profoundly affecting the livelihoods of billions of people in East Asia, whose very survival depends on predictable rainfall for agriculture. The last El Niño also brought 9 powerful atmospheric rivers to the western United States, colossal currents of moisture streaming through the air. These led to major transportation issues, dangerous landslides, and widespread flooding, overwhelming infrastructure, and disrupting daily life. You can think of an atmospheric river like a river of moisture, thousands of miles long and several hundred miles wide, streaming through the air with immense volumes of water vapor. When these atmospheric rivers reach land, they are forced upwards by mountains cool and release all that moisture, causing monumental precipitation, drenching the landscape. Everywhere on Earth, the profound shift in water circulation is felt during El Niño. However, the specific changes you experience in your local weather conditions may be completely different from the changes another person sees in their local weather elsewhere on our planet. El Niño typically brings a reversal of the normal conditions for a given area. This is why places like East Asia or the Amazon rainforest, which typically get plenty of rain, will experience parching drought during an El Niño event, their lush landscapes turning dry and brittle. Or why usually dry climates like Western North America will experience tremendous rainfall events, transforming arid lands into temporary wetlands. The profound impact is undeniable, but its manifestation is regional and varied. The recent El Niño event was also directly responsible for significant worldwide shipping delays in 2023. This occurred because there wasn't enough water to feed the Panama Canal, a vital global trade artery. The canal, which relies on consistent rainfall to keep its locks filled and accommodate all of the colossal cargo ships hoping to pass through, faced critical water shortages, leading to immense queues and economic disruptions. It was a stark reminder of how interconnected our global systems are, where a distant climate phenomenon can ripple through international commerce. El Niño is described as the warm part of the ENSO cycle because Pacific sea surface temperatures are higher than average during this time, spreading warmth across vast oceanic expanses. In addition to changing worldwide weather patterns, this also negatively affects sensitive ecosystems. Take, for example, coral reefs, those vibrant living cities beneath the waves. They rely on particular stable sea surface temperatures to survive and support some of the most important and biologically diverse life on Earth. Corals have a symbiotic relationship with tiny colorful algae called zooxanthellae, which live within their tissues and provide them with food and their vibrant hues. But an increase in water temperatures, even by a few degrees, can cause the coral to expel this algae, leaving it drained of color and vulnerable. This is known as coral bleaching. A reef can recover from this bleaching if conditions improve in time if the water cools back down. But their risk of dying is high, and the last El Niño event was no exception. An unprecedented 99.7% of Atlantic tropical reefs were impacted by bleaching level heat stress during the 2023 to 2024 El Niño event, as part of the fourth worldwide mass bleaching event in recorded history. It was a silent, devastating tragedy unfolding beneath the waves, a stark warning of the ocean's vulnerability. The warmer Pacific waters and weakened trade winds from El Niño also caused the upwelling of cooler, nutrient-rich water to temporarily slow or stop, as we discussed earlier. This leads to a dire situation where less phytoplankton means large numbers of fish must migrate or perish, their food source dwindling. As you can imagine, this ripples across the entire food chain, impacting other animals from marine mammals to seabirds. For coastal families and communities who rely on those fish for nourishment or income, this El Niño effect can be devastating, hitting at the very core of their livelihoods and traditions. Now that we've discussed what it's like during a neutral ENSO period and the destructive changes that can happen with El Niño conditions, like we saw in 2023 and 2024, what can we expect from the upcoming La Niña phenomenon? La Niña is the other extreme, the cool phase of this vast oceanic oscillation. This period is marked by stronger than usual trade winds and cooler than average Pacific sea surface temperatures. While El Niño usually causes the reversal of neutral conditions, bringing drought to wet areas and floods to dry ones. The best way to understand La Niña is to think of it as a more intense version of neutral conditions for most parts of the world, a normal plus, as we called it though, with a few nuanced exceptions. During La Niña, the neutral columns of rising warm air above South Asia and Eastern North America become even more pronounced, leading to increased rainfall and storm activity, while the typical column of warm air above Africa reverses, leading to different regional impacts. Just as your experience of El Niño is highly dependent on where you are located on the globe, the same is true of La Niña. Its effects are a complex tapestry weaving different patterns across continents. As of August 2024, the U.S. National Oceanic and Atmospheric Administration NOAA predicts a 66% chance that La Niña will develop between September to November of 2024, a clear signal from their models, and there's a 74% chance that it will last well into the Northern Hemisphere's winter of 2025 to 2026, suggesting a prolonged cool phase. As of this contemplation, models are predicting a roughly 50% chance that this La Niña event will peak at a moderate strength. However, while forecasts for a La Niña event happening are usually correct, the predicted strength for these events will likely change from month to month, reminding us that climate prediction is a dynamic, evolving science. A strong El Niño ending in 2024 does not necessarily mean the upcoming La Niña will be as extreme. Sometimes, a strong El Niño leads to a strong La Niña, but other times, a strong El Niño is followed by a weak La Niña. With only 10 times in the historical record where the ENSO has changed between El Niño and La Niña within a one-year time period, as is expected with this year's switch, there just isn't enough historical data to draw many definitive conclusions about how the strength of one phase predicts the next. Besides, scientists wisely warn that the strength of an ENSO event does not always directly line up with the severity of its impacts. A moderate event can sometimes cause significant disruption if other factors align. So, what do we know more specifically about the upcoming La Niña? For the northern part of North America, La Niña typically brings with it a colder, wetter winter with increased snowfall and lower temperatures, a true embrace of winter's chill. While the southern part of the continent might experience a warmer and more dry winter, a subtle reversal allowing for milder temperatures and less precipitation. And notably, La Niña will increase the likelihood of a more active hurricane season in the Atlantic, creating an environment more conducive to storm formation with the potential for more and stronger hurricanes requiring heightened vigilance along coastal regions. For East Asia and Australia, this typically means a significant increase in rainfall, bringing relief from drought, but also the potential for flooding and intensified monsoon seasons. While in Africa, La Niña can mean some areas to the west are more wet, receiving abundant rains. Eastern Africa tends to experience more drought, creating challenges for water security and agriculture. The connection between ENSO and Europe isn't quite as clear. Since the continent is further from the source of the oscillation in the Pacific, its effects are more subtle and indirect. But La Niña is expected to bring lower than average temperatures to Central and Western Europe, with less precipitation across the mainland this winter, and more precipitation to the north and south, a complex interplay of atmospheric forces. There's one final profound thing we need to talk about when it comes to La Niña predictions, and it adds a layer of complexity to our understanding. The El Niño and La Niña extremes of the ENSO have been happening for millennia, part of Earth's ancient natural rhythm. But what's less certain, and a subject of intense scientific inquiry, is how global warming from climate change will impact this cycle. While we see short-term localized temperature swings from ENSO, the all-over trend of global warming continues relentlessly on an upward trajectory driven by human activities. This means we are entering uncharted territory, a planetary experiment unfolding before our very eyes. There's clear evidence that as our planet continues to warm from climate change, the occurrence of severe weather will escalate, its intensity growing. But the ENSO is a complicated worldwide, and in many ways, still an unpredictable phenomenon, its nuances still being deciphered by science. Just in recent history, El Niño and La Niña events have become stronger and more frequent, leading to more intense droughts, more devastating floods, more widespread heat waves, more destructive wildfires, and more extreme storms. This was profoundly evident during the last La Niña event, which lasted for an unusually long 3 years from 2020 to 2023, leaving a significant imprint on global weather. Exactly how global warming may impact the ENSO cycle in the long term is unclear, a complex area of ongoing research. But we do know that climate change is likely to amplify the impacts of ENSO, making its extremes even more extreme. A warmer baseline means that even a normal El Niño could bring unprecedented heat to certain regions, and even a normal La Niña could intensify existing drought or flood patterns. Luckily, life on our planet is nothing if not resilient and adaptable, having survived countless changes over billions of years. And as our world continues to change and experience the millennia-old ENSO swings, scientists will learn more each year, collecting new data, refining their models, and enhancing their understanding of this complex climate system. The approaching La Niña will undoubtedly teach us more about our planet's climate, adding another chapter to this ongoing story of discovery. Let's hope we are paying attention, absorbing these lessons, and using them to adapt and prepare for our future in sustainable ways. The quiet wisdom of the Earth, etched in its cycles, always has something to teach us if we are willing to listen. I'd love to hear in the comments what questions you have about our planet's climate, or perhaps your own observations of its changing rhythms. Thanks for sharing this quiet moment of contemplation. Making this video, or rather crafting this narrative, required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astromans on Patreon and your continued engagement. A huge thank you to everyone who has signed up and supported this gentle journey of discovery. If you'd like us to make more videos like this, more quiet explorations into the wonders of our world, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team, becoming part of our growing community of curious minds. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time. When I started my Milankovitch cycle contemplation with a reference to Game of Thrones, I didn't realize exactly how apt my analogy was, how deeply its fictional narrative resonated with the unseen realities of our planet. In that television show, the armies of the Night King in the north are trapped behind a giant wall, a colossal barrier of ice and magic, holding back an existential threat of unending winter. And just like in the TV show, it turns out that on Earth, there exists a powerful icy force to the north that is constantly seeking to overthrow its bounds and rush southward. That powerful winter, a biting chill of immense scale, is also kept at bay by a mighty unseen wall, one that allows the nations to the south to enjoy relatively tranquil temperate conditions, a gentle reprieve from the deep cold. And just like in the TV show, that wall on occasion eventually gets breached, leading to a wave of ice and biting cold that sweeps down and threatens the lives of all those in its way. You might not immediately recognize what I'm talking about. Where is this wall? This magnificent invisible barrier? And what is the icy winter it protects us from? The answer to the first question is a name that I find particularly cool. Imbued with a sense of cosmic power and mystery, the polar night jet. And it turns out that the icy force it protects us from the polar vortex is a biting chill, not to be underestimated, a phenomenon that has in recent years whispered its name into our daily news. What exactly is this polar vortex, this swirling mass of frigid air? And how does the polar night jet, this unseen shield, protect us from its icy embrace, keeping its vast power at bay? Join me now as we gently learn more about this climate-shattering phenomenon and contemplate what happens whenever the polar night jet breaks down, unleashing the polar vortex upon unsuspecting lands. It is a story of profound atmospheric forces silently shaping our world. There are actually two polar vortices, immense swirling masses of cold air, one at each pole of the planet, a northern polar vortex and a southern polar vortex. They are like giant invisible gyres, constantly present over our planet's cold extremities. And even there, each vortex comes in two distinct parts, like layers of a magnificent invisible onion, each playing a vital role in the intricate dance of Earth's atmosphere. First, there is the tropospheric polar vortex, a powerful cyclonic swirl of air, spinning in the section of the atmosphere closest to the ground, the very layer where we live and breathe, known as the troposphere. This is the familiar realm of our daily weather, where clouds gather, rain falls, and winds blow. This layer extends from ground level up to about 10 to 15 kilometers, or roughly 6 to 9 miles high. It is within this layer that a staggering 75% of the total mass of the atmosphere resides, making it the densest and most active part of our aerial ocean. Above that, quietly residing in its own serene realm, lies the stratospheric polar vortex. This is a technically separate weather phenomenon, dwelling in the calmer, higher reaches of the atmosphere, the stratosphere. It has its own immense size, its own grand seasonal cycle strengthening in winter and weakening in summer, and a profound, though often indirect influence on the global climate, interacting subtly with its lower counterpart, the tropospheric vortex, like a higher-level conductor guiding the orchestra below. Each of these massive cyclones sits serenely over its respective pole, spinning in majestic synchronicity with the planet's rotation. Imagine our Earth as a colossal spinning top, and these vortices as the great unseen caps at its very ends, turning along with it. Within their vast swirling currents, wind speeds can reach astonishing velocities up to 240 kilometers per hour, or about 150 miles per hour. This is a truly immense force, a silent, powerful river of air that shapes the very environment above the poles. But why do these powerful winds happen? What orchestrates this magnificent swirling dance of cold air? The first crucial piece of the puzzle lies in temperature difference, the fundamental driver of so much of Earth's weather. Imagine our planet as a grand canvas painted with varying degrees of warmth. At locations like the equator, where sunlight is most concentrated, striking the Earth's surface most directly and powerfully, the air is warmed intensely. As it warms, it becomes lighter, less dense, and naturally starts to rise like a gentle, unseen breath, escaping from a vast heated surface. This upward movement of warm air creates a zone of low pressure beneath it, a subtle invitation that gently draws air into it from its surroundings. Much like a giant, silent vacuum cleaner, steadily humming across the land, drawing in air from all directions. Conversely, at places like the poles, where the sun's warmth is diffused and gentle, striking the surface at an oblique, glancing angle, the air is much colder. This frigid air is denser, heavier, and naturally contracts, gently falling back towards the surface of the Earth, drawn down by gravity. This creates zones of high pressure, where air molecules, feeling the gentle press of their neighbors, wish to spread out to expand into available space, like a crowd of sleepy school children. Finally released into a wide open field after a long day of confinement, eager to disperse. So naturally, with these two fundamental forces constantly at play, the powerful rising warmth at the equator and the subtle, persistent falling coolness at the poles, there is an inherent tendency for air to rush from the high-pressure poles towards the warmer, low-pressure region of the equator. Imagine freezing cold winds, born of the deepest chill, constantly trying to escape from the North and South poles, yearning to find warmer, more expansive homes, a relentless, powerful flow of air, seeking equilibrium. However, as we discussed in our previous contemplation about global air circulation, this simple model is a little too basic, a mere sketch of a much grander masterpiece. For wind does not simply travel in one continuous straight line from the pole to the equator. Instead, because air rising from the equator begins to cool and descend much sooner than expected, around a latitude of 30 degrees both north and south, where it creates subtropical high-pressure zones, and similarly air from the poles warms and rises earlier at around 60 degrees latitude, creating subpolar low-pressure zones. The atmosphere resolves itself into 3 distinct cells of air circulation in each hemisphere. These are the graceful Hadley cells, which operate closest to the equator, where warm air rises and flows poleward before cooling and descending. Then there are the polar cells, which operate at the highest latitudes, where cold air at the poles descends and flows equatorward before warming and rising. And nestled between these two, like a quiet intermediary, is the Ferrel cell. Unlike its temperature-driven companions, the Ferrel cell is not directly powered by heat differences. Instead, it is gently dragged along by the rotation of the Hadley and polar cells, much like a quiet gear in a vast unseen clockwork, and it rotates in the opposite direction to their motion. In terms of our northern polar vortex, which we are focusing on, this means that once the cold air from the pole begins its journey southward, driven by the pressure gradient, it eventually encounters warmer wind, traveling in the opposite direction. And when two vast air fronts, born of different temperatures and moving in different directions meet, they don't simply mix and blend seamlessly. Oh no, they clash like two grand opposing armies, meeting on an invisible battlefield, creating powerful boundaries and defining distinct zones. So the polar vortex, even in its normal state, finds itself gently contained, bounded, clashing softly against winds coming in from all sides, a dynamic equilibrium of opposing forces. But there's more at play here, a second profound force that truly redirects those winds, spinning them into the powerful vortex that keeps them circling the poles, rather than rushing directly down towards the equator. Where does this majestic spin come from? It's due to something known as the Coriolis force, that subtle yet powerful consequence of Earth's rotation that we've touched upon before. In a simple imagined flat world, cold wind from the poles would indeed travel directly towards the equator, while warm wind from the equator would simply float over it towards the poles. But the world isn't a simple flat sheet. It's a majestic rotating sphere. You are traveling right now wherever you are at a certain speed due to the Earth's rotation. If you're at the very pole, your eastward speed is virtually zero, merely rotating on the spot like a quiet pivot. But if you're at the equator, you're moving eastward at a breathtaking 600 kilometers per hour. You might not notice this fact because everything next to you, the ground, the buildings, the very air, is on average traveling at the same speed, in the same direction, like passengers on a smoothly gliding ship who only perceive relative motion. But imagine what happens if you or a vast parcel of air were to travel from the equator towards the pole. The principle of conservation of momentum gently whispers that you would still be traveling eastward at roughly the same speed as previously carrying that initial momentum. But suddenly, as you move poleward, the Earth beneath you is not traveling quite so fast in an eastward direction. Remember, at the pole, you'd have zero eastward speed, simply rotating slowly. So, if on the other hand, you manage to keep all your eastward momentum from the equator and travel towards the pole, suddenly it will appear compared to everything else moving at a slower eastward pace, like you are traveling east really fast. This apparent deflection is the Coriolis force in action. In practical terms, this profound principle means that air that travels up towards a pole from the equator, whether towards the North Pole or the South, will not go straight up. Instead, over large distances, it will start to curve gracefully towards the east. This rapidly eastward traveling air is why you get jet streams. These are not just currents of air. They are powerful invisible ribbons, vast rivers of wind carving precise paths across the skies. They are like fast-flowing, sinuous currents in the atmospheric ocean. There are at least 4 of these magnificent high-altitude rivers of air gracefully straddling the gaps between the atmospheric cells we just discussed. The subtropical jet stream lies between the Hadley cells and the Ferrel cells, a little weaker, a gentle whisper of the wind's power located around 30 degrees latitude. But the jet streams we are primarily interested in, those formidable forces that shape our winters, are the polar jet streams. These are powerful rings of fast-moving air embracing the frigid air that develops in the North and South Poles, typically found around 60 degrees latitude. These majestic ribbons of air encircle the globe in an almost continuous undulating path, a little underneath the boundary that separates the troposphere where our weather occurs and the stratosphere, the calm layer above, approximately 10 kilometers up. They are surprisingly thin, only a few kilometers deep, like a delicate thread drawn across the vast canvas of the sky. Yet they can be hundreds of kilometers wide, a vast unseen highway of wind stretching across continents. And in their very hearts, the wind can surge to astonishing speeds, reaching up to 400 kilometers per hour. As a gentle reminder, speeds over 120 kilometers per hour are already considered to be the strength level of hurricanes. These are truly colossal forces shaping the very air around our planet with unseen power. The jet stream around the South Pole is remarkably stable, more consistent in its embrace than its northern counterpart. Its powerful winds overrule the polar winds, trying to leave the polar air mass whipping them along with it and gently dragging the entire polar cell into a massive Antarctica-spanning vortex. This stability is partly due to Antarctica's unique geography, a large cold landmass surrounded by ocean, creating a more consistent, contained swirling of air with fewer major landmasses to disrupt its flow. This means that the southern polar vortex rarely strays dramatically from its icy domain. At this point, a keen-eyed observer might have noticed a subtle yet intriguing flaw in this model. If the conservation of momentum means that air going from the equator towards the pole gracefully veers towards the east, why is it that air traveling from the pole towards the equator doesn't do the exact opposite? After all, it has virtually zero momentum, moving to zones that have considerably more momentum comparatively. It should logically be quickly left behind, appearing to start spinning to the west, a powerful countercurrent. This is a perceptive question, and indeed it is true. However, cold winds, as they begin their journey from the pole, encounter much more friction. As this dense, heavy air starts to slide underneath the warmer front, seeking its path towards the equator, it also drags along the ground, interacting with the Earth's surface and topography. This constant friction seems to slow it down enough that the powerful countervailing jet stream, circling high above, gently overrules it, maintaining the overall eastward flow. It's important to note this subtle tension at play, though, for it becomes much more important in the phenomenon we call the polar night jet. The polar night jet is the specific jet stream that elegantly bounds the vortex at the North Pole. Particularly, it bounds the stratospheric polar vortex, the upper layer of the swirling cold air. It is the invisible wall, the magnificent guardian that keeps the most frigid air masses safely contained during the coldest part of the year for the North. During the winter months in the North, the sun, our great source of warmth, is absent from the sky entirely for extended periods. This prolonged lack of sunlight creates even more intensely freezing temperatures, a profound chilling of the air, as heat is constantly radiated into space without solar replenishment. Interestingly, this colder climate creates a deeper pressure difference between the air around the pole and the air further south, and this enhanced pressure gradient actually strengthens the very forces that create the polar night jet, making it an even more formidable wall, a more robust containment system. Meaning that during the coldest part of the year, this vast freezing air is usually remarkably well contained, a testament to the strength of its atmospheric prison, a natural barrier against the deepest cold. However, as with all things in the delicate dance of Earth's climate, this containment does not always hold true. There are forces subtle and grand that can disrupt a jet stream, causing its steady path to waver and buckle. Imagine a powerful river flowing smoothly, suddenly encountering obstacles. Certain zones on Earth, like the vast dynamic boundary between sea and land, where two vastly different surfaces meet and exchange energy, can create their own localized winds, which can subtly tug at the jet stream like gentle eddies, pulling at a powerful current, diverting its flow. Similarly, the imposing presence of a large mountain range, a colossal upheaval of the Earth's crust, acts as a physical barrier. It doesn't just block the wind. It forces an entire air current to elegantly move around it, creating ripples and diversions in its otherwise smooth flow. These atmospheric waves, known as Rossby waves, can travel great distances and interact with the jet stream. Even other powerful weather phenomena like El Niño, which we touched upon earlier, can have a profound, subtle impact on the path the jet stream chooses to take, altering the global distribution of atmospheric energy. It is a reminder that everything is connected, and a change in one grand system can gently nudge another, leading to unforeseen consequences. The jet stream, in its essence, is not fixed rigidly in place. It is a dynamic balancing point, a continuous negotiation between a range of opposing forces. When it encounters such obstacles, or when the subtle atmospheric pressures shift, it causes it to subtly deviate from its course. And once it begins to deviate, it is like a vast invisible string that has begun to bounce, to oscillate. It shifts no longer perfectly in its delicate balance and overcorrects itself, then finds itself out of balance again, leading to another overcorrection. This creates immense, slow-moving planetary waves like giant ripples spreading across the atmosphere. These are the graceful undulating movements that cause the polar night jet to gently meander around the Earth. Rather than traveling in a perfectly straight line, its usual elegant curve replaced by a more erratic path, like a river winding through a vast plain. And these elegant oscillations can at times reach a point where there is a breach, a moment when the invisible wall gives way, allowing the frigid air to escape. The first gentle sign of this profound shift often comes in the form of a phenomenon known as a sudden stratospheric warming SSWOs. Most common in late winter, an SSW is ironically a rapid and dramatic warming event in the stratosphere directly above the pole. Temperatures can rise by as much as 50 degrees Celsius over the course of just a few days, a dramatic, almost unbelievable thermal inversion, where the normal cold of the stratospheric winter is replaced by unexpected warmth. Something within the intricate system of the jet stream can be so thrown by this dramatic event that it leads to the southward moving westerly winds overpowering the jet stream, partially or completely reversing its flow. The powerful eastward flow falters, then struggles, and sometimes incredibly begins to move in the opposite direction. This reversal of the jet stream, this fundamental shift in its core, is the key that unlocks the polar vortex. No longer contained by its majestic guardian Arctic wind, that deep ancient chill born of the polar night suddenly moves south, spilling out from its usual icy domain as it encounters warmer and warmer air driven by the intense pressure gradient. It pushes faster and faster south in an attempt to balance the profound temperature difference. The entire jet stream buckles its elegant curve, transforming into a series of profound loops and dips like a rope being whipped. And suddenly, it pivots massively, reorienting itself traveling down the planet so that regions like Europe and America, usually safely on the warm temperate side of the polar night jet, suddenly find themselves squarely in the domain of the polar vortex. The forces of winter in their purest, most biting form have truly arrived, an Arctic blast sweeping across densely populated areas. In fairness, not all of these events are devastating. With sufficient preparation, you can simply put on some warm clothes, bundle up against the cold, or try to avoid going outside for the month or so that the polar winds are overhead. As long as you're ready for the cold, as long as you respect its power, it's not the end of the world. It's merely a temporary challenging visitor, a period of heightened vigilance. However, sometimes the outcome is far more serious, etching itself into the collective memory of a region. A stark reminder of nature's formidable power when its balance is disturbed. Consider the UK in 2009 to 2010. During what became known as the Big Freeze, the parts of Scotland experienced temperatures as low as 22 degrees Celsius, the coldest in nearly 40 years. This brought widespread transport disruption, grinding travel to a halt as roads became impassable and train lines froze. It caused event closures and power failures that left many in the dark and cold, struggling to keep warm. Sadly, this intense cold, this sudden powerful breach of the polar night jet, in turn, led to the tragic death of 25 people, a somber reminder of the human cost when such natural phenomena occur. In the U.S., the 2019 January-February North American cold wave saw a polar vortex move down across much of the country, bringing similar devastating outcomes. Some areas saw temperatures as low as 50 degrees Celsius. If you take into account the wind chill factor from the blustery freezing winds exposure, could cause frostbite in just 10 minutes, a terrifyingly short span of time. Snowstorms raged, blanketing regions in deep snow, and life itself seemed to slow to a crawl as cities became ghost towns and schools closed. Sadly, another 22 people died during this event, with hundreds more needing urgent frostbite treatment. The raging polar vortex, in its unrestrained southward push, was responsible for this profound disruption, a powerful and undeniable display of Earth's colder side. In time, the imbalances in the global temperature restore themselves. The vast atmospheric forces gently realign, and the jet stream eventually returns to its previous position, pulling the polar vortex back into its familiar contained domain over the pole. However, it's worth noting that some level of jet stream breakdown occurs in the north approximately 6 times every decade, making these events a relatively regular, albeit often subtle feature of Northern Hemisphere winters. They are not entirely rare occurrences. If you live in the Northern Hemisphere, you will likely see many more of these events over the course of your lifetime, although hopefully not all as powerful and impactful as these two profound examples. In the South, you are likely safer. There have only ever been 2 instances in recorded history of the southern polar jet stream breaking down in the same way as the northern one, a testament to its greater stability. It has happened, though, and the precise mechanisms behind its rare breakdowns are not fully understood, adding another layer of mystery to our climate systems. A subtle reminder that even with all our knowledge, nature still holds profound secrets. It's difficult to say, as global temperatures gradually rise due to human activity, what influence this might have on the jet streams themselves. Some evidence indicates that they are traveling further poleward on average, year on year perhaps, in response to a warming Earth that shifts atmospheric patterns, although this is apparently not unheard of in the planet's long history. There is some more evidence that the jet streams have actually strengthened since 2002, perhaps making them more resilient. If so, we should be grateful. Although unpleasant, the biting cold of the polar vortex usually is only a passing weather phenomenon. We see it return north within a month or so, a temporary inconvenience. But if the jet stream were to permanently go, if that magnificent unseen wall were to truly collapse and stay breached, the polar vortex would come down from the north to stay, and we would truly know what it is like to live in Arctic conditions, a profound, permanent winter for much of the globe, a scenario that pushes the boundaries of our current understanding and future predictions. The more I've learned about this subject, the more I've discovered that the winds of our planet are this fascinating, intricate weave of interplaying forces and effects that tug and pull on each other, constantly seeking perfect balances, and yet constantly shifting in rhythms and patterns. And yet, it does so practically invisibly. So much is going on that we simply do not see down here on the ground, just because air is, well, air, a transparent, often unnoticed medium. And yet, I've learned its profound importance. The polar night jet is not just wind with a cool name. It is a bastion of protection, a formidable wall against the frozen wind, silently safeguarding our temperate lives. It really makes you think of the incredible majesty of the world around us. How much is going on that protects us, that we simply do not see, an unseen ballet of cosmic and atmospheric forces constantly at play, maintaining the delicate habitability of our precious home and inviting us to a deeper sense of wonder and humility in the face of such natural power.